Hello and welcome to this specialisation on TensorFlow 2 for deep learning. My name is Kevin Webster and I'm a Senior Teaching Fellow in the Department of Mathematics at Imperial College London, and I'm delighted to be here teaching this course. I'm also joined by a fantastic team of graduate teaching assistants who are PhD students here at Imperial, and they'll be helping me throughout the course to guide you through all the amazing things you can do with this library. TensorFlow is one of the most popular libraries for deep learning. It's a project that was released as open source by Google back in 2015, and it's widely used today amongst researchers and professionals at all levels. There are a few things I'd like to emphasize and make clear right at the beginning about this course in this video. The first thing is that this isn't a course on deep learning. It's going to be assumed that you already have knowledge of deep learning models, and this course is really just about learning TensorFlow 2. The second thing I'd like to emphasize is that this course is intended for both people who have worked with TensorFlow 1 before and people who are completely new to TensorFlow. You don't have to have had any prior experience at all in order to take this course. And just in case you're feeling daunted by the prospect of local installations or working on remote servers or training on GPUs, you don't need to worry about any of that in order to learn how to build, train and use deep learning models in TensorFlow. In this course, everything that you need is available here on the Coursera platform, and you can complete the course entirely through the browser. The way this course is structured is a combination of lecture videos and practical coding tutorials, so you'll be putting all of the content you learn about into practice straight away. You'll be developing deep learning models for a range of applications, including image classification, text sentiment analysis, regression tasks, and generative language models. At the end of each week of the course, there'll be a programming assignment where you'll need to apply the concepts you've learned from that week. The programming assignments are all in Jupyter notebooks, and you'll complete and submit them entirely through the Coursera platform. In addition, at the end of each one of the courses in this specialization, there's a capstone project. These capstone projects are extended projects that will include material from throughout the course to stretch your knowledge of working with TensorFlow even further. The capstone projects are peer assessed, so you'll be able to give and get useful feedback from your peers. So I hope this gives you a good and clear idea of what this course is about and what you can expect. I really hope you'll find this course useful and a lot of fun to work through. And I'm looking forward to seeing you in future videos. Hi, and welcome back. In this video, I'd like to set the scene for what we're going to be looking at in this week of the course. The first week of the course will be a different format to the following weeks, and that's because before we start diving into learning TensorFlow 2, I'd like to give something of an overview of some of the important developments and concepts, differences from TensorFlow 1, and introduce some resources and tools that I think you'll find really useful, such as Google Colab, and of course the TensorFlow documentation. There are also several items this week that you'll see are marked as optional. These items cover things like how to install TensorFlow on your local machine, or different ways that you can use TensorFlow, or how to upgrade code you might have written in TensorFlow 1 to be compatible with TensorFlow 2. Now, you don't need to work through any of these optional items in order to take this course. As I mentioned in the introduction video, you can complete this course entirely through the browser. These optional items are included as extra resources to those of you who would like to make use of them. You can feel free to skip these items if you want to. You can always come back to them later on if you want to prepare your own setup. There's also no programming assignment in this first week, but there will be one at the end of every week from next week onwards. So, that all being said, let's get started. From next week onwards, the structure of this course will be a combination of lecture videos from me, where I'll be explaining and presenting the different features and objects in TensorFlow, and coding tutorial videos given by one of the graduate teaching assistants, or GTAs, where the material I'm presenting will be coded with examples into a tutorial notebook here on the Coursera platform. In these coding tutorial videos, the notebook itself is available to you as a separate item in the course shell. You can open up this notebook in a separate window, so you can code in the examples yourself as you follow along with the GTA in the tutorial video. This is great practice to get comfortable with coding things up in TensorFlow for yourself. The coding tutorial video and notebook immediately following this video will give you a taster of how this is going to work. This is going to be the format for much of the course content following this week. So please go ahead and open up the following coding tutorial video and notebook, and Jerome will take you through a first Hello World example in TensorFlow 2.
Hello and welcome to TensorFlow 2 for Deep Learning. My name's Jerome. I'm a PhD student here in Imperial College London's Maths department. I'm also one of the GTAs that will be running the coding tutorials for this course. Delighted to meet you. As Kevin has already told you, in this lesson we will go through a Hello World example in TensorFlow. We'll import TensorFlow using a Coursera notebook, we'll check its version, and then we'll run a short script that trains a neural network. Let's get started. Open the Coursera notebook for this lesson. You should see what I have on the screen now. Start off by importing TensorFlow and checking its version. To import TensorFlow, write import TensorFlow STF, then press Shift and Enter to run the cell. In the cell beneath, type out tf._version_. Press Ctrl and Enter to run the cell. You should find that you've imported TensorFlow version 2. The cell at the bottom of this notebook contains code that creates and trains a neural network to classify images of handwritten numbers taken from the MNIST dataset. Don't worry about the details of this code for the time being. You will understand it by the end of next week's lessons. All it does is load a dataset, declare a model, and train that model. Run the code by clicking on its cell and pressing Ctrl and Enter. The dataset should take about 30 seconds to load, so be patient. Maybe make yourself a cup of tea. Once the dataset is loaded and the model begins to train, you'll see a printout informing you of the model's training progress and its performance. When the model is finished training, the printout will tell you that the model is trained successfully. Congratulations! You've just trained your first model using TensorFlow 2. If the code in this notebook is unfamiliar, don't worry. The concepts underpinning it will be discussed in future lessons. In this lesson, we were simply checking that you could run TensorFlow 2 on Coursera. I'll see you in the next tutorial.
Welcome back. In this video, I'd like to talk about some of the big changes that have been made in the version 2 release of TensorFlow. As I mentioned in the introduction video, TensorFlow 2 is a big step forward from TensorFlow 1, and the focus from the TensorFlow development team has been on making it really easy to use, without losing the benefits that the paradigm of TensorFlow 1 gave us. Also, I just want to repeat one point from that video, which is that you don't need to have used TensorFlow 1 before to succeed in this course. But even if you haven't used TensorFlow 1 before, you might find it useful to know a bit about how your code would have been organised in this earlier version, and why, because it will illuminate some of the advances of TensorFlow 2 and give you more of an idea of what's going on behind the scenes. If you've ever worked with TensorFlow 1 before, then what you can see here might look familiar to you. Straight away it looks quite complicated and confusing. In TensorFlow 1, you'd first have to set up the variables and the operations that define your model, as well as maybe a loss function and optimizer you want to use to train the model, so that everything is in place before you can actually run anything. So you couldn't immediately use these variables w and b that I've created up here. Instead, these variables and operations would define a computational graph that basically says how the inputs, outputs and parameters of your model are all connected. And you'd also have to define these things called placeholders that serve as entry points to your computational graph where you can feed the data into. Once the graph is built, you could then run the graph inside something called a TensorFlow session. But first you'd need to initialize your variables before you could use them. Then you could run the training operation and calculate the loss, passing in the data with something called a feed dict. TensorFlow 2 does away with a lot of these complications, so I'd like to summarize some of the major developments in TensorFlow 2 that makes your workflow a lot easier. Eager execution already existed in TensorFlow 1, but in TensorFlow 2 this is now the default behavior. Eager execution means that TensorFlow variables and tensors can be used straight away. There's no need to run an initializer or to launch one of those session objects to get their values. It sounds like such a simple thing, but this is really quite a big change from the whole graph building and running in a session paradigm. In TensorFlow 2, Keras has become the default high-level API for TensorFlow. So the complete Keras API is now wrapped up as part of the TensorFlow installation and has become seamlessly integrated with TensorFlow. The nice thing about Keras, as we'll see later in the course, is that it's really easy to use, but it's still very flexible. Even though I say it's the high-level API for TensorFlow, you'll be able to do most, if not all, of your model developments using Keras. The final thing I want to mention is that the API in TensorFlow has had quite a lot of work. Before, there were a few inconsistencies and things like functions in different places doing very similar things and so on. In TensorFlow 2, this has been considerably cleaned up. As you'll see later when we take a look through the documentation, it's nicely organized into modules and it makes it much easier to find what you're looking for. There's of course a lot more that's new in TensorFlow 2 that I haven't touched on here, but I wanted to highlight some of the major changes. As I say, even if you've never worked with TensorFlow 1 before, I hope this gives you a bit of context for TensorFlow 2 and also gives you a sense of what's going on in the background. Remember that with the graph building paradigm, the main purpose is to optimize the code so that it runs faster. In TensorFlow 2, this is actually still happening, but it's happening behind the scenes, for example, when you use the high-level Keras API, so you don't have to worry about it. But when you become a more advanced user of TensorFlow and start writing lower-level code, you'll see later on in the course how you can still gain the benefits of compiling parts of your code into a single graph for performance gains. So it's helpful to at least be aware at this stage of the graph compilation that's going on in the back end of TensorFlow. I'll see you in the next video. Welcome back. In this course we're going to be exploring TensorFlow 2 and some of the amazing things that you can do with it. As I mentioned in the previous video, TensorFlow 2 is quite a big step forward from TensorFlow 1. And so to help us explain some of the changes in TensorFlow 2, I'm delighted in this video to introduce Lawrence Moroney. Lawrence, thank you for being here today.
Thanks for having me.
So I'd like to talk about some of the features in TensorFlow 2, but before we get to that, maybe you can talk a bit about what you do now. So you're an AI advocate at Google right now.
That's right, yes. So I lead a team of what's called scalable advocates for AI at Google. We've got a number of folks around the world where our job is to inform and inspire developers around the world, as well as advocating for them. So as Google are building our products to make sure that we build it how developers want it.
Okay, so tell me a bit more about how it all started for you. How did you get into AI in the first place?
Well, that's actually an interesting and very long story. And it was, for me, it began with an experiment run by the British government way back in 1992. You know, and I know you're from England, so have you heard of it?
No.
I'm putting you on the spot. So back in 1992, England was in the midst of a pretty big recession. And the government was planning various schemes to get out of recession. And one of the things was they identified that AI was a possible thing for industry of the future. So they wanted to find 20 people. And I grew up between Ireland and Wales, and I was living in London at the time. And they wanted to find 20 people who were qualified, who had college degrees, but who were unemployed. And I was one of the 20. And to train us up in AI, and then we could maybe be the spearhead of a future set of consultants or startups or something like that to help industry with AI. Unfortunately, it failed, but I got bitten by the AI bug. And so then a few years ago, while I was working at Google, the bug bite came back, and I was working on a product called Firebase. And Firebase has a technology called Firebase Predictions. So if you're building a mobile application, you can use Firebase predictions to predict things like when your users are going to churn, or maybe when your users are going to do in-app purchases, that kind of thing. And that uses TensorFlow as its underlying technology. So I helped launch Firebase predictions. Then I got bitten by the AI bug, like I mentioned again, and I was able to go and join the TensorFlow team, and here I am.
That's great, great story.
Thank you.
So over the years, you must have seen a lot of changes in the technologies that ML researchers are working with. How do you see the impact of technologies like TensorFlow? How has it changed machine learning and deep learning research and the way we do it?
I think the biggest impact for me is to widen access, to give it accessibility to AI and AI technology to far more people. Like I mentioned, for me, back in 1992, I was part of this core group of 20 people that the government had selected, and it was a massively privileged position to be in because the technology, and it was like Prolog and Lisp, and compilers for that were very expensive and very few people could do it. Nowadays, technology is a lot cheaper, and things such as Python are open, and TensorFlow is open source, so that far more people can be involved. And having more people involved trying to solve any problem is always a greater way of solving a problem than having fewer people involved. So to me, I think that's been, beyond the technology, one of the biggest impacts has been, the fact that it's open source, that it's free, that anybody can start using this.
Right. And so talking about TensorFlow 2 specifically now, what do you think are some of the big changes, big developments that excite you the most?
So I come from a software development background, so it's going to be viewed through that lens. And so TensorFlow 1 was terrific in that, but it was very oriented towards researchers. It wasn't very intuitive to a typical software developer to load everything into a graph and then execute that graph. We're used to executing line by line. So with TensorFlow 2 being eager by default makes it a lot easier for the general software developers. And there's a stat that I always like to cite that research showed that there were about 300,000 AI practitioners in the world, but there are close to 30 million software developers. And if we can build a product and a platform that appeals to the 30 million as well as the 300,000, that to me is the kind of thing that busts you out of the hype cycle, that makes it a real thing. And there isn't another AI winter from 1992 until nowadays, that if you have it becoming part of the de facto toolbox of the 30 million people. So to me, that eager by default in TensorFlow 2 is the #1 feature that excites me.
Yeah.
And then of course, on the theme of widening access and making it easier, things such as Keras. So being able to define neural networks using Keras layers, to be able to define an LSTM with one line of code and that kind of stuff, again, on the theme of widening access, making it easier for people to be productive with machine learning is what I'm most excited about.
Right, that's really cool. And so looking to the future, what do you see as the future direction of AI and TensorFlow and so on?
Yeah, so I think the future direction is the continued widening. Right, more and more technologies coming into it, making them easier for developers to use. I know you're going to be teaching about probability in this course, so things such as probability 2-3 years ago, you probably needed a PhD just to understand the documentation, but having APIs that make it easier for people to be able to use things such as TF probability, and you'll be chatting with Paige about that in a later video, which is really exciting. And so that to me is where the future I see is going, that general level of widening access, plus the ability to deploy your models in new places. So being able to deploy models to mobile devices, so you can now have inference in the palm of your hand, being able to have cheap and easy deployment of models to the cloud so you can scale to billions. And that type of thing means that it's out of the hands of the few and into the hands of the many. And when that starts to happen, that's when the magic really grows. And
that's great.
Hopefully that's the road that we're on.
Yeah. Well, Lawrence, thank you for joining me today.
Thank you.
One of the resources you should definitely be aware of that makes it really easy to develop with TensorFlow, as well as other libraries, is Google Colab. If you haven't heard of Colab before, what it is a research project by Google that was publicly launched in 2017, and it provides a free cloud-based service where you can write and run Jupyter notebooks entirely through the browser. The really cool thing about working with Colab is that you can get up and running with it straight away. Many of the popular libraries that you might want to use come pre-installed, including TensorFlow. And if you want to install additional packages, you can also do that. So it takes a lot of the pain away for you. And it comes ready with a GPU that you can use for your networks. And this makes a big difference when it comes to developing deep learning applications. As to train large networks and use large datasets, you really need accelerator hardware. We've made all of the coding tutorial notebooks in this course available on Colab, as well as on the Coursera platform. Now, it's not necessary for you to use Colab for any of the course. You can complete the course entirely through the Coursera platform. But you might find that for some of the more computationally demanding deep learning models that you work with, using the free GPU on Colab saves you a lot of time waiting for networks to train. So in this lesson of the week, I'd like you to familiarize yourself with Colab so that you have it available as an extra resource to work with. The first stop you might like to make is to the welcome page of Google Colab. I've added the link to this page in the resources. This page is itself a Colab notebook, and it already demonstrates some of the interactive features that you get with the notebook environment. Down here, you can see that there are some useful links to resources for learning the workflow with Colab notebooks, including working with Markdown, installing libraries, working with data, and so on. In the following tutorial video, Jerome will demonstrate these and other important features that you'll want to know about when working with Colab notebooks. The other nice thing is that you can use Google Drive to store data that you want to use in the development of your deep learning model and link that directly to your Colab notebook. This is something else that Jerome will demonstrate in the following tutorial. So if you haven't used Colab before, I'd highly recommend to step through the following tutorial video and just take some time to familiarise yourself with it. I'm sure you'll find it a valuable resource. And when you're ready, I'll see you in the next video.
Hello! As you've heard from Kevin, in this tutorial I will be your guide to Colab, Google's cloud-hosted version of the Jupyter Notebook. Colab offers a GPU hardware acceleration that will be useful to you throughout this course and beyond. To reiterate what Kevin said, creating a Google account is free and you'll need one to get the most out of Colab. Let's jump in. We'll pick up right where Kevin left off, with the Welcome to Colab notebook. Sign in to your Google account via the link in the top right-hand corner of the page. Enter your username and password. You are now using Colab with your Google account. To create a new notebook, click File, New Python 3 Notebook. An empty Python 3 notebook should open. Notebooks in Google Colab are saved to your Google Drive. To see where your active notebook is located in your drive, click File, Locate in Drive. You'll then be taken to the notebook's location. You can see that by default, notebooks are saved in a Colab Notebooks folder. To create a Colab notebook while browsing your drive, alternate click, go to More, and then Google Colaboratory. You've probably already noticed that the Colab interface is very similar to that of a Jupyter Notebook. Colab does indeed provide similar functionality to that of a Jupyter Notebook. For example, you can create a code cell below the active cell by pressing Ctrl-M followed by B. You can switch a cell from code to Markdown by pressing Ctrl-M, then M, and return it to a code cell by pressing Ctrl-M and Y. As with Jupyter, Markdown cells in Colab support text formatting. To write a header, for example, you just need to prepend your text with a hash symbol. If I switch this back to a Markdown cell by pressing Ctrl and M, then Enter to edit the cell, and finally, hashtag Hello Colab. An important aspect of Google Colab is that the notebook runs on a remote machine that is owned by Google. This means that you don't need to have Python installed locally for Colab to work, but you do need a persistent internet connection. If you want to change the notebook's kernel language or the host's hardware configuration, go to Runtime, change runtime type. You can then choose between Python 2 and Python 3, and between 3 hardware accelerations. The default instance, None, has 13 GB of RAM but does not have a GPU. The GPU instance, on the other hand, has a Tesla K80 GPU and the same amount of RAM as the default instance. The final instance type, TPU, is a Tensor Processing Unit instance, which offers a TPU rather than a GPU. I won't talk about TPUs in detail now, but you should know that TensorFlow 2 does not currently support TPUs, at least at the time of this recording. This is likely to change in the future. We won't be talking about TPUs on this course. Now let's load some data into Colab. To load a dataset that is on your Google Drive, you need to mount your drive to the notebook. Do this by opening a code cell and typing out from google.colab import drive and drive.mount G drive. Press Shift and Enter to run the cell. Click on the URL that it returns allow access to your Google account, then copy the authorization code into the cells dialog box. Drive will take a few seconds to mount to Colab. You'll know it's done when you can see your drive in the left-hand pull-out tab under Files. You can see that in my drive, I have a text file called hello.txt. I can deduce this file's path from its location in the tree. To load this file, I'm going to use Python's open function. I'll type out my file equals open gdrive /my drive /colab notebooks /hello.txt. To print the contents of the file, I'm going to write print myfile.read. Press Shift and Enter to run the cell. As with Jupyter Notebooks, you can run bash commands inside the code cells of a Colab notebook. To run a bash command, prepend the command you want to run with an exclamation mark. To list the files in your working directory, for instance, you would write !ls and then run it by pressing Shift and Enter. You can use bash commands to install any packages that are not installed on the Colab instance already. If I thought NumPy was not installed, I could install it via the command !pip install NumPy. As you can see, NumPy is already installed on the Colab instance. At the time of this recording, TensorFlow 1 is installed on Colab by default. This will probably change in the future. But to upgrade to TensorFlow 2, run the command !pip install TensorFlow equals 2. The upgrade should take about 1 minute. I sped the footage up to save you some time. When the install is complete, click Runtime, Restart Runtime. Once the runtime is restarted, check TensorFlow's version by importing it and running the command tf:\version:\. We can see that version 2 is now installed. Colab will probably be upgraded soon to feature TensorFlow 2 by default, in which case you won't need to install it each time you launch a new notebook. In addition to creating notebooks from scratch, Colab can open a Jupyter notebook that is on your local machine. To do this, click File, Upload Notebook. You can also load Jupyter or Colab notebooks that are saved on your GitHub. Just go to GitHub. Enter your username and password, and then select the file that you want to load. If you want to download a Colab notebook as a Jupyter notebook, click File, Download.ipynb. You are now familiar with the ins and outs of Google Colab. Who says there's no such thing as a free lunch? If you should find yourself waiting a long time for a model to train on your local machine, or on the Coursera notebook, then I suggest you try the GPU-accelerated Colab notebook. I'll see you for our next tutorial.
Welcome back. One of the important resources I would definitely encourage you to make use of throughout this course is the TensorFlow documentation. We're going to be covering many different areas of the TensorFlow library within this course, and the way the course is structured means it's quite self-contained. But I'm sure that you'll still find it useful to go back to the TensorFlow documentation as a reference, to remind you of syntax or function signatures, or to explore more of the options that are available in a particular part of the library. So it's a good habit to get into straight away to familiarize yourself with the documentation. To browse the TensorFlow documentation, just head to tensorflow.org. Along the top here, you can see the link to the API documentation. And by the way, there are some great tutorials and the TensorFlow guide that you can find through this link. So make sure to take a look at those too. But right now, we want to take a look at the docs. And if you hover over the API link, you can see the different versions of the API docs. We're going to take a look at the latest stable release, which at the time of this recording is version 2.0. On the first page, you can get an overview where you can look through all of the modules that are within the library, and you'll see there's quite a few here. Further down the page, there are the classes and the functions listed. If I scroll down to the bottom, you can see the other members where you'll find things like TensorFlow types. Okay, so on the left-hand side of the page, you can find all these classes and functions listed in alphabetical order, and you can click through to see the documentation for any of these. Now, if I just minimize this list, you can now see an overview of the many modules within TensorFlow. There are two modules in particular that I want to draw your attention to, as we'll be using them a lot in this course. The first one is the tf.keras module, which we're going to start using straight away. If we open up this module to see what's inside, you'll see there are some classes at the top here, input, model and sequential, and you'll see what all of these are later on in the course. And there are more modules I can take a look at within the tf.keras module. And again, you can click through any of these to bring up the documentation. The other module I want to point out, if I just minimize the tf.keras module, is the tf.data module. This is another important module within TensorFlow, and we'll be looking at this further on in the course when we get to talking about data pipelines. So please take some time to explore the documentation, if only for the moment just to familiarize yourself with how it's laid out. You should think of it as a companion resource to what we're going to cover in this course, and I'd always encourage you to look up the documentation for the different objects that you're learning about throughout the course. So with that, I look forward to getting started building our first deep learning models in TensorFlow in the next week of this course. Hi, and welcome back. In this section of the week, we'll take a look at the different options for installing TensorFlow. As I mentioned in the first video of the week, this section is entirely optional. You don't need to install TensorFlow locally in order to take this course, so feel free to skip these videos if you don't want to have to bother with a local installation, or if you already have TensorFlow installed. In my experience of teaching courses, I've often found that installing TensorFlow is actually the first thing that students get unstuck with, and it can be quite confusing as there are a few installation options, and it also depends on the operating system and what hardware you have available. The different options for installing TensorFlow are documented on the website if you head over to tensorflow.org/install. Broadly speaking, the main factors are the operating system you're running, whether it's Linux or Mac OS or Windows, and whether your machine has a GPU available that you'd like to use for training. You'll notice the site also mentions Google Colab over here as well, which is another option for using TensorFlow that we've covered earlier in the week. Down the left-hand side, you can see some different options for installation, and in the following videos, Jerome will walk you through the pip installation and using Docker containers for running TensorFlow. The pip installation is probably the easiest one, especially if you'll only be using the CPU version of TensorFlow if you don't have a graphics card that you want to use. It's a bit more work if you want to install the GPU version of TensorFlow, as there are additional drivers and libraries you have to install in this case. You can find more details about this in the GPU support guide, and you can see the link for this down the left-hand side. The recommended method for enabling GPU support is with Docker containers. If you haven't worked with Docker before, then just to give you a quick overview, Docker is software that you can install and run on your machine, and what it does is to create objects called containers that have an isolated virtual operating system, where, for example, TensorFlow and other libraries can be installed, whatever is needed to run TensorFlow programs. These containers are created from Docker images. The images are what define the libraries and packages that are installed inside the container. You can download the official TensorFlow Docker images for whatever version of TensorFlow you want, whether it's the GPU or the CPU version, or if you want Python 3 support, or a specific version of TensorFlow, and so on. Note that the GPU version is Linux only. The nice thing is that by using these images, you avoid any problems of conflicts between library versions and installation issues that might be specific to your machine or operating system. In the following two videos in this section, Jerome will show you examples of installing TensorFlow using pip into a virtual environment, or with using a Docker container to run TensorFlow. These videos assume that you're comfortable working with the command line and that you've had some experience of working with Docker before. Just to reiterate, these tutorial videos are totally optional. If all this sounds too intimidating, then don't worry about it, just feel free to skip through. You don't need to make a local installation to complete this course. But if it is something you'd like to get set up, then I hope you'll find Jerome's tutorial videos helpful. And I'll see you in the next section.
In this tutorial, I will show you how to install the CPU variant of TensorFlow on an Ubuntu machine. We will install virtualenv, a virtual environment manager, create a virtual environment to install TensorFlow 2, then install TensorFlow using pip, a Python package manager. If you have Conda installed and are comfortable using it to create and activate a virtual environment, then you may prefer to use this instead of virtualenv. I've also linked an install guide in this video's description. Let's get started. Open the link to the TensorFlow install page that is in this video's description. You'll see that 3 TensorFlow 2 packages are available: TensorFlow, TensorFlow GPU, and TF Nightly. The first of these is the CPU-only variant of TensorFlow. This is the simplest to install and is the one that we will be installing in this tutorial. We'll return to TensorFlow GPU in a future lesson. If you scroll down, you'll find that this page also lists TensorFlow 2's system requirements and hardware requirements. You should have Python 3.4 or greater, and pip version 19 or later. To check these, open the terminal and type in pip -- version. As I mentioned, you should have at least version 19.0. To check the version of Python 3, type in Python 3 -- version. Anything from Python 3.4 will work. Download and install the latest version of virtualenv for your user account by running pip install --user -u virtualenv. Virtualenv will then download and install. Next, create a virtual environment that uses Python 3 using the command virtualenv and then the name of the environment that you want to create. I'm going to call mine tf2env. Press enter, and the environment will be set up. To activate your newly created environment, run source, then the name of the environment, followed by bin/activate. You can see that the environment's activated by this parenthetical expression at the beginning of the line of the terminal. You can then install TensorFlow 2 in your environment using the command pip install TensorFlow equals 2.0. If you haven't used a virtual environment before, you may wonder why we are using one. Virtual environments allow you to neatly maintain multiple versions of a single package, or even of Python, on your machine. So if you wanted to, you could have one environment for TensorFlow 1 and one environment for TensorFlow 2. Once the download and install is completed, open Python 3 to verify TensorFlow. Type import TensorFlow as TF to import TensorFlow, and check its version by typing tf._version_. And there you have it. We've installed TensorFlow 2 locally. Knowing how to create and use virtual environments is a useful skill, especially if you use Python regularly. Giving thought to environment creation at the start of a project can save a lot of time later on. This tutorial was entirely optional. You don't need to use your local install of TensorFlow to follow along with the course. If anything, I would recommend using either the Coursera notebook or Google Colab. That way you can save your work remotely, and your local computer's resources will remain available while you run tasks remotely. I'll see you in our next tutorial. Hi, Jerome here again. Last time you learned how to install TensorFlow 2 for CPU locally. In this tutorial, you will learn how to run TensorFlow GPU via a Docker container. I'll walk you through installing the Docker engine, installing your NVIDIA drivers and the NVIDIA Container Toolkit, and creating a TensorFlow GPU container. I'll be using a computer in Imperial's cluster that is running Ubuntu and has access to a NVIDIA GPU in this example. The install procedure that I show you will only work on a Linux machine with a NVIDIA GPU. If you're working on Mac or Windows, then you'll need to install the dependencies of TensorFlow GPU directly. I've included a link in this video's resources that shows you how to do this. Let's start by installing the Docker engine. Open up the first link in this video's resources, the one to the About Docker webpage. Here, select your distribution of Linux in the left-hand drop-down menu. This will take you to an Install How-To page, which will tell you how up-to-date your OS needs to be to support Docker, and how to install the Docker engine. I'm using Ubuntu 18. If you're using a different variant of Linux, you should follow the install instructions for it, then skip to the section of the video where we install the NVIDIA Container Toolkit. We're now going to install the Docker engine. Add the Docker engine's key to Apps Key Manager and its repository to the repository index via the first command in the text file attached to this video. Great! apt can now see the Docker repository. Update the package index and install the Docker engine and container using the command that I'm pasting into the terminal now. Once that's done, you can verify that the Docker engine is installed correctly by running the hello world image. To do this, write sudo docker run hello world. This command downloads a test image and runs it in a container. When the container is running, it prints a message and then exits. At this point, you have installed Docker and made its repository visible to apt, so that it will update each time you run apt update and apt upgrade. Let's now install the NVIDIA Container Toolkit. You should already have installed the NVIDIA GPU drivers that you need. If you haven't, you can install the ones that are recommended for your GPU by running the command sudo ubuntu drivers auto install. As you can see, my system already has its drivers installed. To check that the drivers are installed correctly, run the NVIDIA System Management Interface. This will only be able to read the GPU information if the drivers have installed correctly. To launch the interface, run the command nvidia-smi. You can see the GPUs on my machine, along with their usage statistics. Now that we have the Docker engine and the NVIDIA drivers installed, let's install the NVIDIA Container Toolkit. The toolkit allows a Docker container to interact with the host machine's NVIDIA GPU. To install the toolkit, add the repository key and the repository address to apt. You can do this using the command that I'm pasting into the terminal now. Once that command is run, use apt-get update and apt-get install to install the most recent version of the NVIDIA Container Toolkit. If you then restart Docker, using the command sudo systemcontrol restart docker, then you are now ready to run a container that uses your system's GPU. Test that the previous steps have been successful by creating a container running NVIDIA's system management tool, nvidia-smi. You can do this using the command that I'm typing into the terminal now. All being well, this will list your GPUs. The difference between the interface you see now and the interface you saw earlier is that this one is being run from inside the Docker container. This tells us that the container is able to access our GPUs. By contrast, the interface we saw earlier was run directly and did not require the NVIDIA Container Toolkit. Now that Docker is set up and you can use the GPUs, let's run a TensorFlow container. To recap, a Docker image is an executable software package that contains everything you need to run an application. A running version of a Docker image is called a Docker container. refer back to the TensorFlow documentations page on Docker. You can see that several Docker images are available for you to use. You will probably want to use the latest stable version of TensorFlow GPU. Tailor the TensorFlow image that you download using the tags. There are tags to enable GPU support, TensorFlow for Python 3, and include Jupyter. We're now going to issue a command that creates a directory, then mounts that directory to a container that is running a Jupyter notebook. To create the directory, run mkdir, and then the name of the directory. I'm going to call mine my Jupyter notebooks. Then to create a container that has access to TensorFlow 2, is using your GPUs, and launches a Jupyter notebook on startup, write sudo docker run --gpus all -it -p, then 8889:8888, then -v, then the name of the directory you want to mount to the container. In my case, it's this my Jupyter notebooks directory, :/tf, then the name of the Docker image that you want to use. We're going to use TensorFlow /TensorFlow : latest GPU Pi3 Jupyter. The -p argument of this command will expose the container's Jupyter port 8888 on our host's 8889 port. This allows the host machine to access the Jupyter Notebook server that is running inside of the container. The -v argument mounts our host's directory to the container's TF directory. If the machine that Docker is running on is local, then you can open Jupyter by going to localhost :8889 in your browser and copying in the token that is printed by the server when it starts up. Since the machine I am running the container on is remote, I need to do something slightly different. I'm going to forward the remote machine's 8889 port to my local 8888 port, which I can do by running ssh-n-f-l localhost 8888 :localhost 8889, and then the name of my remote user. I type in my password and enter it. Then when I open up my browser and go to localhost :8888, copy in the token generated by the server when it started up, then I can create a new notebook and check that I have access to TensorFlow 2, along with the GPUs on my host machine. So we've been able to verify that we can run TensorFlow 2 using a Docker container. When you're finished, you can stop your container running by going to the terminal containing it, pressing Ctrl+P, Ctrl+Q, then writing sudo docker container ls, extract the container ID for your container, then paste that into the command sudo docker stop at the very end. So like this, sudo docker stop, and then the container ID of the container I want to kill. This tutorial contained a lot of information. You learned how to install 3 pieces of software: the Docker engine, the NVIDIA drivers, and NVIDIA Docker, a package that allows Docker containers to access their host GPU. Having installed these, you then created a Docker container using a TensorFlow GPU Docker image. This container ran a Jupyter notebook, which you connected to remotely using port forwarding. Finally, you verified the entire procedure by importing TensorFlow 2 and checking that it could see your GPU. Great job. I'll see you in the next tutorial.
Welcome back. If you've worked with TensorFlow 1 before, you might already have lots of code written for TensorFlow 1 and are understandably concerned about all of your code becoming unusable if and when you upgrade to TensorFlow 2. The good news is that the TensorFlow development team have made the process of converting your current code to be TensorFlow 2 compatible really easy. You can find some useful information on migrating from TensorFlow 1 to TensorFlow 2 in the TensorFlow guide. If you first navigate to tensorflow.org/guide, then down the left-hand side here, you'll see an item Migrate from TF1 to TF2. On this page, you'll find a lot of useful information for TensorFlow 1 users about porting your code over to TensorFlow 2. The first item you can see here is about an automatic conversion script that has been made available to convert existing TensorFlow 1 code to be TensorFlow 2 compatible. Jerome will show you an example of using this upgrade script in the following tutorial video. The one thing I'd like to point out here, though, is that this upgrade script will make your legacy code compatible with TensorFlow 2, which will save you a lot of time and means you can continue running your code after the upgrade, but it can't transform your code to use the TensorFlow 2 syntax or idiom. It relies heavily on the tf.compat.v1 module you see here to update your code. That means that things like placeholders, sessions, and so on will still be there in your code, but they'll now be using the tf.compat.v1 module. So that's why, if I just go back to the first page, there is more information here on upgrading your code to the native TensorFlow 2 style. I won't go through all these points now, but you can see the kinds of things they're addressing, replacing session.run calls, placeholders, and so on. Down here is a really striking illustration of just how much simpler TensorFlow 2 is to use. This is TensorFlow 1 code, which creates a very simple graph that is just an affine transformation of the input, and you can see we've got the TensorFlow 1 placeholders, variable scope, down here is the session object, and underneath is the variable initializer. In the TensorFlow 2 style, this code can be written like this. And you can see straight away just how much simpler and intuitive this code is. No need for placeholders, sessions, or feed dictionaries. We're just defining a simple function that depends on variables w and b, and then running it. If you do have legacy TensorFlow 1 code that you'd like to upgrade to TensorFlow 2, my recommendation is to first run the upgrade script on your code so that it continues to work with the TensorFlow 2 installation. Then I would leave it as it is and work your way through this course. During the course, the style and syntax of TensorFlow 2 will become more and more intuitive, and after completing the course, I'm sure you'll find the information in the TensorFlow guide much easier to understand, and I think it'll become much more obvious how you should go about upgrading your code. So on that note, I'll pass over to Jerome now, who will show you an example of using the upgrade script, and I'll see you in the next week of the course.
As you just heard from Kevin, I'm going to show you how to use the TensorFlow upgrade function, tf_upgrade_v2. You'll see that although the upgrade function makes our original code compatible with TensorFlow 2, it does not take advantage of its shift to eager execution. What we're going to do is we're going to create separate virtual environments for TensorFlow 1 and TensorFlow 2, test our script to upgrade in TensorFlow 1, then use tf_upgrade_v2 to upgrade it, before finally checking that the upgraded script works in TensorFlow 2. Let's get started. We're going to create two virtual environments, one for TensorFlow version 1.14 and one for TensorFlow 2. To do this, write virtualenv -p python3 tf1 and virtualenv -p python3 tf2. Activate the TensorFlow 1 environment by running source tf1/bin/activate. Install TensorFlow 1 via pip install TensorFlow equals 1.14. It will take around 30 seconds to install, so you should know that my footage is sped up. Once it's done, deactivate your current environment by running deactivate. Then activate the TensorFlow 2 environment, tf2, via source tf2/bin/activate. install TensorFlow 2 using the same procedure as before, pip install TensorFlow equals 2.0. You should find that the install takes around 30 seconds. In my current working directory, I have a TensorFlow 1 script that initializes and trains a linear regression model. I provided the script in this video's resources. Download it and place it in your working directory. If you open the file, you can see that the code follows the graph and session paradigm of TensorFlow 1. When upgrading a script from TensorFlow 1 to TensorFlow 2, it's important to verify before conversion that the code runs in TensorFlow 1. Activate the TensorFlow 1 environment. Then run the script by typing Python 3 linear regression tf1.py. The printout from this script tells us that TensorFlow version 1.14 was imported successfully and that the script ran to completion. Having checked that our script runs in TensorFlow 1, we are now going to show that it does not run in TensorFlow 2, then upgrade the script using the tf upgrade v2 function. Switch to the tf2 environment. Try running the script again. It will fail, since the script contains code that hasn't been dressed for compatibility with TensorFlow 2. To upgrade the script, we're going to use the tf upgrade v2 function. To use it, type tf upgrade v2, pass the name of the file you want to upgrade to the argument infile, which in this case is linear regression tf1.py, and pass a name for the upgraded file to the argument outfile. I'm going to use linear regression tf2. The function prints out a summary of the changes it made during the upgrade. If you print the contents of your current working directory using ls, you'll see that the function has output two files, the upgraded Python file and a log file. If you open the log file, you'll see that it contains a summary of the parts of the code that have been altered. If you then open the upgraded script, you should find that it has been adapted for compatibility with TensorFlow version 2. Note that although the new code is compatible with version 2, it does not take advantage of its major changes, such as eager execution. This is an important point, since TensorFlow 2 defaults to eager execution. If you try running the upgraded script using TensorFlow 2 via Python 3 linear regression tf2.py, you'll find that it fails to run. This is because the code relies on graph and session type execution. To enable this, and to therefore disable eager execution, open the upgraded script and add the line tf.compat.v1.disable eager execution. Save and close the script. Try to run the file again. And you should find that this time it runs successfully. We've succeeded in upgrading a script from TensorFlow 1 to TensorFlow 2. You now know how to upgrade your TensorFlow 1 code for compatibility with TensorFlow 2. Hopefully what you've learned in this lesson will save you from rewriting any monster scripts you may have in TensorFlow 1. This is our final lesson of the week, so it is time for me to say goodbye. I've enjoyed teaching you, and good luck with the rest of the course. Goodbye!
Welcome to this week of the course on TensorFlow 2. So now that you've got everything set up, you're ready to dive into TensorFlow and start building your first models. As I said before, in TensorFlow 2 a big drive has been towards ease of use. At the highest level, the easiest way to start building deep learning models in TensorFlow is to use the Keras API, and that's what we're going to begin focusing on. In this week, we're going to introduce the Keras Sequential API and use that to build our first models, as well as train them and make predictions from them. Along the way, you'll see how you can select different optimizers to train the networks, different loss functions depending on the task, and how to keep track of any number of metrics during the training. Throughout the course, there'll be a combination of lecture videos where I'll be presenting new things to you and demonstrating them on slides. And there are also coding tutorial videos where a graduate teaching assistant, or GTA, will take the new concepts and APIs that I'm introducing and put them into practice in a tutorial notebook. There'll be a different GTA each week for the coding tutorials, and this week Sergio will be going through the sequential model API tutorial with you. By the end of the week, you'll have everything you need to design, build, train and make predictions from your own deep learning models in TensorFlow. And you'll be putting all that into practice in the programming assignment, where you'll train a computer vision model to classify handwritten digits using the MNIST dataset. So let's get started. Throughout the course, we'll be using the Keras API within the TensorFlow library to develop models. So let's just start by talking about what Keras is. The Keras project was authored by François Chollet, and it's a high-level neural networks API, developed with the specific goal of making it easy to build, train and infer from deep learning models. It was developed as an API without a backend, and actually supports multiple backend implementations. In TensorFlow 2, it's been adopted as the high-level API. And despite being high-level and easy to use, it's still very flexible. Probably 99% of the time, whatever you want to do, you can achieve it using the Keras API. So we'll be using it extensively throughout this course. You can visit the Keras homepage at keras.io, where we can read more about the Keras project and its development principles. There are also some nice guides and tutorials on here to take a look at. So when you install TensorFlow 2, you get all of this packaged up as part of the library in the namespace tensorflow.keras. And that's what we're going to be using throughout the course. You can also see this if you browse the API on tensorflow.org. Here you can see tf.keras, and within that is the Keras library. So you can see there are two sources of documentation you can refer to, but I'd recommend using the TensorFlow documentation as your go-to reference. Welcome back. In this video, we're going to introduce the Keras sequential class and use it to build simple models. In fact, you'll probably find that most of the neural networks that you work with can be built using the sequential class, and it's a really easy and intuitive way to construct deep learning models. We're going to be using the sequential model throughout this course, so let's take a look at how to use it. First, take a look at our imports. We import the sequential class from tensorflow.keras.models, and here we're also importing the dense layer type from tensorflow.keras.layers. The way we build our model is really simple. We just create an instance of the sequential class. Here I'm calling the instance model, and all we do is pass in a list of Keras layers. So this model is a feed-forward network with a single hidden layer. You can see that when you create a dense layer, you always have to say how many units should be in that layer. And that's what we have here in the first argument. You can also optionally pass in an activation, like I've done here, so the hidden layer has a ReLU activation. If you don't pass in anything for the activation, the dense layer will have a linear activation or no activation by default. The output layer has 10 units and is using a softmax activation. You can imagine this might be a model for a classification task where there are 10 classes. One thing you might have noticed is that we're not saying what size or shape the input's going to be. So if you think about it, with this model definition, we don't yet have enough information to create all of the model's weights and biases. And it's actually okay to do this and leave it until the training stage, when you feed the data into the model, before the weights and biases are created. Alternatively, you can explicitly tell the model what shape the input data will be at the build stage. Like here, I'm specifying that each input data example will be a one-dimensional vector of size 784. Now, in this case, the weights and biases will be created and initialized straight away. Here's an alternative way of building the exact same model. Instead of passing in a list of layers, you can use the model.add method to append additional layers to the model. So what we have on this slide is an equivalent model to what we had on the previous slide. Which method you choose is, I think, largely just a matter of taste, but it might also depend on how you structure your code. For example, you might find it useful to add layers one at a time, like I'm doing here, if you want the model building code to depend on some conditions or loops or something like that. Here's one last example before you put this into practice yourself. In this model, I'm importing two layer types, flatten and dense. You can see that I'm making the first layer a flatten layer, and again I'm giving the input shape to the first layer in my model so that the weights and biases are created when I define the model instance. Notice that the input shape here is two-dimensional, and so that's why I'm flattening each data input to unroll it into a long one-dimensional vector of size 784 before sending it through to the first dense layer. So now you've seen how to build sequential models, it's time to code some examples yourself. As I mentioned in the introduction video, there'll be coding tutorial videos throughout this course where a GTA will walk you through a tutorial notebook to practice what I'm covering in these lecture videos. In the Coursera shell, you'll see the tutorial items following my lecture video marked as coding tutorial, and there will always be a video and a notebook item. In the video, you'll meet the GTA who will take you through the tutorial notebook. As you can see, this week Sergio is doing the coding tutorials. There are several coding tutorial video items during the week, and in each video the GTA will take you through a section of the coding tutorial notebook. It's a good idea to open the coding tutorial notebook in a separate window so you can follow along with the screencast and code in the examples yourself. Of course, you can pause the screencast at any time and try some things out for yourself in the notebook. It's there for you to experiment with. So go ahead and open up this week's notebook now, ready for the following coding tutorial.
Hello, my name is Sergio and I'm a PhD student at Imperial College London. I'll be teaching the coding tutorials of this week. With Kevin, you have seen how to apply keras to construct a sequential model. Now it is your opportunity to build your first neural network in TensorFlow. Firstly, open the notebook. Inside there is a skeleton of the code that you will fill during the tutorials of this week. Let's see how we can do this. At the top of the notebook, you can import TensorFlow and show its installed version. In the next cell, you can import the sequential model and the relevant layers for this coding tutorial. After this, you can go to the next cell to start creating a sequential model. Let's begin by adding to our model 3 dense layers, as you have done in the last lecture video. The layers have to be written one after another inside the sequential model. The first 2 are going to have 16 units with a ReLU activation function, and the last one 10 units with a softmax activation function. Once you are done, try to print now the weights of the model by calling model.weights. What happens when you run it? Well, it seems that it is giving us an error in model.weights. It is due to the fact that the weights are not yet initialized, as you didn't specify the input shape. You can solve it by specifying the input shape, and you can do it with a new flattened layer. Let's indicate as input dimensions 28 × 28, which are the ones of the MNIST images that you will employ in the assignment of this week. Now when you run the cell, you can see that the weights are initialized. You can even read the dimension shape of the weights. There is, however, a nicer way of printing the layer information of a sequential model. you can use model.summary to show a table with the main features of each of the layers. Why don't you try it? Try changing model.weights by model.summary. If you run the cell, you will see a table containing the flattened layer and the 3 dense layers. The columns in the table indicate the layer type, output shape, and number of parameters or weights in each layer. Below you can find information about the total number of parameters to train. With all this information in mind, now you can play a bit with the sequential model. For instance, you can substitute the softmax activation function in the last dense layer by a new softmax layer. Note that the default activation function for the dense layer is linear. If you now run model.summary, you can check that the output is identical as the previous one. In addition, you can try to define a name for each layer. For instance, let's call layer 1 to the first layer. You can see that this name now appears in the summary. So well done! You have just created your first neural network. As you have seen, the sequential model is really easy to use. Now it is your chance to explore it a bit further. Why don't you try setting up other activation functions for the dense layers, such as the hyperbolic tangent or the sigmoid function? You can even add more types of layer to our model. With Kevin, you will learn how to implement the convolutional and pooling layers within the sequential model of Keras.
Hi, and welcome back. Now you know how to build simple neural networks using the sequential model. The models we've built so far were all feed-forward networks, which are also called multi-layer perceptrons or MLPs. In this video, we'll see how to build convolutional neural networks by including convolutional and pooling layers in our model. Here's a typical setup for a convolutional network. I'm importing the flatten and dense layers that we used last time. Plus, I'm also using the conv2D and max pooling 2D layers. And here's the model definition. The first layer is a convolutional layer, and these layers have 2 required arguments. The first is the number of filters, so we have 16 filters in this layer, and the second is the shape of the convolutional kernel. So let's take a look at our input shape. This input could well be an image with 32 by 32 pixels and 3 color channels. So our kernel is convolving over the image with a window of 3 by 3 pixels using 16 filters. We're also passing the output through a ReLU activation function. The second layer is a max pooling layer. This layer has 1 required argument, which is the pooling window size, and that's also 3 by 3 pixels. This is followed by a flatten layer, which remember is unrolling each data example into a long one-dimensional vector ready to be passed through to the final 2 dense layers. So just to make sure we understand what's going on here, let's take a look at the tensor shapes after each of these layers. You'll notice that the first dimension of every tensor has a value of none. And that's because the first dimension will always be the batch size. And that batch size is flexible. We can pass any number of examples in a batch to the model. TensorFlow represents this with the value none in the tensor shape. So let's ignore the batch size for the moment and look at the remaining shape dimensions. Remember the input shape is 32 by 32 by 3. After being processed by the convolutional layer, this becomes a tensor of shape 30 by 30 by 16. The 16 is because we created the layer with 16 filters. The shape 30 by 30 is because these convolutional layers have no zero padding by default. Sometimes you'll hear that referred to as valid padding. And also the default stride is 1, So with a kernel of shape 3 by 3, that results in a 30 by 30 by 16 shaped tensor output. Likewise, the pooling layer has a 3 by 3 window, and these are non-overlapping. So that downsamples the input to a 10 by 10 by 16 shaped tensor. The flatten layer just unrolls this into a one-dimensional vector, ignoring the batch size. So 10 times 10 times 16 is 1600. From here on, the shapes are easy to understand. This is just a dense layer with 64 units, and the final dense layer has 10 units. Here's how it would look like if we wanted same padding. That just makes sure that the spatial dimensions don't change. So the 32 by 32 by 3 shaped input goes to a 32 by 32 by 16 output. And the rest of the shapes for the other layers are the same. And the last thing I want to show you is just a shortcut. Often the window shapes of convolutional and pooling layers have the same size in each dimension. In that case, you can just write the kernel size or the pool size as a single integer. So here, this is the same as writing 3 by 3 explicitly as we did before. In this lecture video, we've seen how to build convolutional and pooling layers into our network. With just these few layers we've seen so far, you can already develop some very powerful deep learning models. So now it's time for you to practice coding up some convolutional neural networks with Sergio in the next coding tutorial.
Welcome back. With Kevin, you have seen how to implement convolutional and pooling layers with a sequential model of Keras. Now it is your chance to put what you learned into practice. Let's see how we can do this. To begin, you can import again the sequential model together with the layers for this coding tutorial. You are going to start by writing a sequential model with different layers. The first layer is a convolutional layer with 16 filters, a kernel size of 3 × 3, a ReLU activation function, and an input shape of 28 × 28 × 1. Once you are done, you can use model.summary to get a description of such a layer. Why is it that you need an input shape of 28 × 28 × 1 and not just 28 × 28? Well, you can try to see what happens when you remove that one. It indeed seems that an error pops up. This is due to the input requirements of the COM2D layer, since that one is necessary and indicates the number of channels in our input. Let's come back to the previous input shape of 28 × 28 × 1 to avoid further errors. Now you can add more layers to the sequential model. Let's continue with a pooling layer of pool size 3 × 3. You can go on and complete your model with a flattened layer and a dense layer with 10 units and a softmax activation function. Now it is your chance to experiment a bit with this model. For example, try setting the padding in the convolutional layer as same, so that you preserve the output dimensions. What happens now when you print the summary of the model? You can see that the input and output spatial dimensions of the convolutional layer are the same. And this is because you use padding equal to same. In addition, try adding a stride of 2 in both the convolutional and pooling layer. Setting a stride equal to 2 means that the stride is 2 in every dimension. Note that a larger stride reduces the output dimensions of the layers. You can check it by running the model.summary as before. Finally, as a last test, you can try to specify the input shape format that you introduce in the convolutional layer. For this, let's remove the padding and strides that you added before. You can modify the format of the input by means of the argument data format. Actually, before we were discussing that you have to write the number of channels at the end of the input shape to avoid errors. This is because the default data format is channels last. Try to define it and you will see that nothing changes in the model.summary. However, you can also define the data format as channels first. And for that case, the equivalent input shape will be 1 times 28 times 28. Remember to also define channels first for the pooling layer to have exactly the same neural network as before. So well done! You have implemented convolutional and pooling layers that are vital in fields like computer vision. You will need to apply them in the assignment of this week to do image recognition at the MNIST dataset. Before finishing, you can explore more the convolutional and pooling layers with Keras. How would you apply other kinds of padding in the COM2D layer? In the next reading, you will learn how to add a weight initializer to a neural network.
Welcome back. So far, we've seen how to build feed-forward and convolutional neural networks in TensorFlow using the Keras sequential class. But to start training our network on data, we're also going to need to define a loss function that will give us a measure of our model's performance and an optimization algorithm. In this video, we're going to talk about how to define these things so we're ready for training. Let's take a look at a simple binary classification network. This model takes a one-dimensional input of size 32, passes it into a fully connected layer with 64 units and an exponential linear unit activation function. That's followed by a final dense layer of just one neuron with a sigmoid activation function. Okay, down here is the new bit of code that we're interested in. This is what is defining the loss function and the optimizer for the network. And as you can see, we're defining the loss function to be the binary cross entropy, which makes sense for this network and task. And the optimizer is SGD, or stochastic gradient descent. These options are being passed into the compile method of our sequential model object. We can also optionally define a set of metrics that we want to keep track of as the model is training. These metrics will be calculated for each epoch of training along with the evaluation of the loss function on the training data. We'll see this in action later when we start training some models. For now though, we just need to know that we can pass a list of metrics into the compile method. So here we're just passing in a list with one metric that is the accuracy. Of course, there are lots of options for each one of these keyword arguments. For example, we could instead choose the Adam optimizer or RMS prop or Ada delta. For the loss function, you could choose the mean squared error, although that might be more appropriate for a regression task, or categorical cross entropy, for example. In the list of metrics, I've added one more. MAE here stands for mean absolute error. So with this call to the compile method, we'd be keeping track of two performance metrics, in addition to the binary cross-entropy loss. One thing that you'll be noticing is that Keras is giving us a really nice, usable interface for setting up these models. and there are a lot of readable strings that we can pass in to many of the options in the Keras API, like we see here in the activation functions, and the options in the compile method. It's definitely worth knowing, though, that each of these strings is a reference to another object or function, and we can always use that object or function directly. For example, all the options I have here in the compile function could be given like this. Instead of passing in the string sgd, I'm directly passing in an sgd object that comes from the tf.keras.optimizers module. Similarly for the loss, the binary cross-entropy loss is available in the tf.keras.losses module. And the metrics I'm using can be given like this. The binary accuracy and the mean absolute error metrics are in the tf.keras.metrics module. The reason why you might want to do this is because it gives you greater flexibility, as many of these objects themselves have options that you might want to have control over. This slide shows you what I mean. With stochastic gradient descent, an important parameter is the learning rate. By default, the learning rate is set to 0.01. But here, I'm creating an SGD optimizer object with learning rate 0.001. I'm also using momentum with a value of 0.9. By default, the momentum value is 0, so there is no momentum. And an extra option I can choose to set is whether or not to use Nesterov momentum, which here I'm setting to be true. Let's take a look now at the binary cross-entropy function. That also takes some options, and here I'm setting the option from logits equals true. If you were watching closely, you might have also seen that I've changed the activation function in the last layer of the network from sigmoid to linear. In other words, now there is no activation function, and I could as well have left this argument out, as the linear activation is the default. And so the network is now outputting the logit, which is any real value before it is squeezed through the sigmoid activation function. The from logits equals true option tells the model that it should take the output of the network, and the loss function itself should handle the squeezing of the output through the sigmoid activation. Mathematically, there's no difference between this and what I had before, but this way turns out to be a more numerically stable approach. Finally, the binary accuracy also has an option, and we can choose what the threshold is for predictions to be classed as positive. The default is 0.5, but here I'm setting it to be 0.7. So now you've seen how to build neural networks as sequential models and set the optimizer, loss function and metrics using the compile method. Once this has been done, you've got everything you need to start training the model on data. And so in the next lecture video, we'll see how to do just that.
Welcome back. With Kevin, you have learned how to define the loss function, metric and optimization algorithm by means of the compile method. These are the last elements that you need before beginning with the training of our neural network. Now it is your chance to put what you learned about the compile method into practice. Let's see how we can do this. You can continue by completing the neural network that you started in previous coding tutorials. Firstly, you can define the compile method with an add-on optimizer, a loss function of the kind sparse categorical cross-entropy, and a metric list containing accuracy. Once you are done, you can now print out the model.optimizer, model.loss, and model.matrix to see what is stored in the model. These are just some choices of arguments that you can take. Indeed, there are plenty of other loss functions, metrics, and optimization algorithms that you may prefer for your particular deep learning application. Let's try to explore now some of these other choices. For instance, concerning the loss function, you have chosen a sparse categorical cross-entropy, because our data labels are integers. On the contrary, if the data labels were one-hot vectors, you could have used categorical cross-entropy. With respect to the optimization algorithm, in Keras you can find plenty of options for it. Some examples are SGD, RMS prop, or ADA delta. There are also many options for the metrics to employ. For instance, try to add mean absolute error, MAE, metric just after the accuracy, if you want to specify more than one metric. As you see, the compile method is very versatile and allows the definition of plenty of loss functions, metrics, and optimization algorithms. However, for some applications, you may want to tune specific parameters. As an example, you may need to control the learning rate of the optimization algorithm. To do this, you need to create an object for the loss functions, metrics, and optimization algorithms. Once created, you can introduce it in the compile method as before. As an example, I am creating an object called opt for the add-on optimization algorithm with a learning rate of 0.005. Then you can pass this object directly to the compile method. Note that you can also print the learning rate of the optimizer if you call model.optimizer.lr. To add more, you can also create an object for the metrics. The objects for accuracy and mean absolute error could be defined in this way. Do not forget to pass the metrics object to the compile method. Don't worry too much about how to exactly define the metric object. In this case, you could use a sparse categorical accuracy for a multi-class classification problem with sparse labels. You will learn more about this during the course. So well done! With the compile method, now you have learned all the basic ingredients to construct a neural network. In the next lecture video with Kevin, you will see how to train it and make evaluations and predictions. Now you can explore more options for optimizers, loss functions, and metrics that the compile method allows. For instance, how would you define the categorical cross-entropy loss function as an object? In the next reading, you will learn more about the matrix available in Keras.
In the previous videos, you've seen how to build and compile models. So now our deep learning model is fully defined. We have the architecture, the number of layers, activation functions, and so on. And we've also assigned an optimizer to the model, possibly with some options of its own, and a loss function, and maybe some metrics to track. So now it's time to train the model. Here we can see each step outlined in code. We've defined a feed-forward network with a 100-way softmax output for a classification task, and we've compiled the model with the RMS prop optimizer, the categorical cross-entropy loss function, and we're going to track the categorical accuracy metric. The last line here shows how simple it is to launch the training. You just need to call model.fit and pass in the training inputs xtrain and the labels ytrain. We're going to assume for now that both xtrain and ytrain are NumPy arrays, where all of the dataset inputs have been stacked together into a single array, xtrain, and all the targets, or outputs, are in ytrain. So the first dimension of each array corresponds to the number of examples in the training set. For example, if each input data point is a one-dimensional array, Xtrain would be a two-dimensional array with the number of samples in the first dimension and the number of features in the second. Ytrain would be a two-dimensional array with the number of samples in the first dimension and the number of classes in the second. Here I'm assuming that the labels have been represented as a one-hot vector, so each row of Ytrain is a vector of length num classes, which is all zeros except for a 1 in the place corresponding to the correct class. Or if all the labels have a sparse representation, so just a single integer for each label, then Ytrain could be a one-dimensional array with a length equal to the number of samples. Notice that in this case we should choose the sparse categorical cross-entropy loss function. Passing these arrays into model.fit will then train the model for one pass through the training data, or one epoch. You'll probably want to train the model for more than just one epoch though, and so here I'm passing in the optional keyword argument epochs equals 10. So the training will make 10 complete passes through the dataset. Another option I want to mention is the batch size. By default, the batch size is set to 32 whenever you pass in the dataset inputs and outputs as single NumPy arrays as we're doing here. If you want to change that to use a different batch size, you can just use the batch size argument. Like here, I'm setting the model to train on mini batches of size 16. There are quite a few more optional keyword arguments for model.fit, and we'll come back to these in future videos where we start to look at more sophisticated features in our training. Finally, an important point is that calling model.fit actually returns something, and it returns something called the TensorFlow history object. This object contains a record of the progress of the network during training in terms of the loss and the metrics that we defined when we compiled the model. This object is actually an example of something called a callback, which we'll look at later in the course. In the following coding tutorial, Sergio will show you how to access the record of the loss and metrics for each epoch of training in the history object. So you're already at the stage of being able to build neural network models, compile them with the given loss function and optimizer, and any additional metrics, and now train them using model.fit. And thanks to the Keras API, we can do all this in just a few lines of code. So now let's open up the notebook again, and in the next coding tutorial, you'll start training your first deep learning models.
Welcome back. With Kevin, you have seen how to implement the fit method of Keras. It allows us to train our neural network with a particular training data. Now it is your opportunity to put what you learned into practice. In this coding tutorial, you will use the popular MNIST fashion dataset. It is similar to MNIST but contains pieces of clothes. Let's see how we can do this. To begin, you can import the packages that you will use during this coding tutorial. After it, let's start by rechecking the sequential and compile methods that you defined in previous coding tutorials. For the sequential model, you have 4 layers. Firstly, a COM2D layer with 16 filters, a 3x3 kernel size, a ReLU activation function, and an input shape 28x28x1. Secondly, a pooling layer with a pool size 3x3. Thirdly, a flattened layer with no specification. And finally, a dense layer with 10 units and a softmax activation function. Concerning the compiler method, you can define an object for the add-on optimizer with a learning rate of 0.005, as well as objects for accuracy and mean absolute error. For the loss function, you can use sparse categorical cross-entropy. You can now proceed to load the MNIST fashion dataset already installed in Keras. This dataset is already split for training and testing, and you can keep the test set to later evaluate the performance of your neural network. This is a moderately big dataset. You can check the shape of the training image to see that it contains 60,000 images of 28 × 28. The labels are integers from 0 to 9, and each number represents a piece of cloth following the order in labels. For instance, you can print the label of the first train image. The label is a 9, which according to our order of labels represents an ankle boot. You can now try to visualize the image to prove that it is an ankle boot. Firstly, in order to ease the learning, you can rescale the images so that they are between 0 and 1, and not between 0 and 255. Then you can display the first image of the training dataset. For this I am using the matplotlib package. You can also print the label of that image to see if it matches the picture. As you can see, it indeed looks like an ankle boot. After this, you are ready to apply the feed method to train the neural network. You can start by setting up the feed method with only 2 epochs. You can also add a batch size of 256, so that the computational time is reduced a bit. When running this line, you will get an error due to the input shape of the train images. This is due to the fact that in the sequential model you specified a channel dimension. To solve it, just add a dummy channel dimension to the training images. After this, you are set to run the feed method. During the epochs, you can see how the value of the loss function decreases. Pay attention also to the values of the accuracy and the mean absolute error that are also updated during the simulation. This takes some time, so I am speeding up the code a bit. You may also prefer not to see the output of the epochs during the training. For it, you can define the verbose parameter, which takes the values of 0, 1, or 2. Adding verbose equals to 0 will silence the printout, while adding verbose equals to 2 prints 1 line per epoch, and verbose equals to 1 is the default one. Let's try to explore now a bit more of the feed method. You can train the model for 8 epochs and save the resulting history object. Again, I am speeding up the simulation, but if you see that it is taking too long, you can reduce the number of epochs or even consider only part of the training data. Once the training is finished, you can start to analyze the history object. It has an attribute precisely called history that is a dictionary and contains information about the loss functions and metrics after each of the epochs. This is quite useful to check how the training is going. For instance, you can try to plot how the loss function decreases after every epoch. From the data frame df, you can create the plots to evaluate how the loss function and metrics evolve after each epoch. I am just going to write here the plot for the loss function, but you can do the same to also plot the different metrics. Once you are done, run the cell and you will see the plot showing how the loss function decreases after every epoch. So well done! You have been able to train your neural network with a dataset of 60,000 images. In the next lecture video with Kevin, you will proceed to use this trained neural network to evaluate how it behaves with the test dataset, and also to make predictions with new images. You can explore more the feed method and all its capabilities. For example, can you plot the metrics of accuracy and mean absolute error during the simulation? Do they increase, decrease, or stay constant? You can continue with the next lecture video to learn more about the evaluate and predict methods.
Welcome back. By now, you've learned how to build deep learning models using the sequential API, how to specify optimizers, loss functions, and metrics using the compile method, and in the last lecture video, you've seen how to train models using model.fit. In this video, we're now going to see how well our network has learned by evaluating its performance on a held-out test set. We're also going to be putting our network into action by getting its predictions on unseen input data. Let's just recap what we've done so far. We defined the model using the sequential class by passing in a list of layers, or remember, you could use the model.add method to add layers one by one. Then we compiled it using model.compile, and there we passed in options for the optimizer, the loss function, and a list of metrics to evaluate the performance of our network with. We trained the model using model.fit, and here remember we're passing in the input data as one big numpy array, xtrain, and the labels also as one numpy array, ytrain. For both of these arrays, the first dimension corresponds to the number of examples in the dataset. Once this has finished training, we have our trained model, and the first thing we'll want to do is test it. Okay, so let's suppose that we have a separate held-out test set of data that we can test it on. This is data that wasn't used in the training, so will give us a good measure of how well the network has learned to generalize beyond the training data. So then, let's say that x tests are the test inputs and y tests are the test labels. Again, each of these arrays contains a number of data examples, and the first dimension of each array corresponds to the number of examples in the test set. Running model.evaluate will iterate over the test set and calculate the loss and the metrics on that test set. So, for example, if we had defined a binary cross-entropy loss function when we compiled the model, as well as an accuracy metric, then this loss function and this metric will be evaluated on the test set and returned by the model.evaluate call. So in that case, we can save those returned values like this. If we had included more metrics, then they would all just be returned by model.evaluate, and we could save them like this. And hopefully, if our model has trained well, then these loss and metric values won't be too far off what we achieved on the training set. So we should use the evaluate method whenever we have a held-out test set like this to evaluate the performance of the network. But if we want to use our trained model to get predictions on unseen data, then we use the model.predict method. This method doesn't take any labels, of course, it just takes in an array of inputs. Here we're going to let xsample be those inputs, so xsample is a numpy array of stacked data inputs. The first dimension corresponds to the number of examples that we want to get predictions for, and the rest of the dimensions will be the data features. In the example I'm showing here, the number of features is 12, and notice how that corresponds to the input shape that I set when I defined the model. Model.predict will then return the outputs of the network for these given inputs. One point that often catches people out, if we're getting predictions on only one example, then we still have to have a dummy first dimension that will be equal to 1. So for example, if xsample is a numpy array with just one input sample, and our network is a binary classifier where the final layer has just one neuron passed through a sigmoid activation, then model.predict will return just one number that we interpret as a probability that the input we passed in belongs to the positive class. Here the probability is very low, so the model prediction would be that this input belongs to the negative class. But see how the output is a two-dimensional NumPy array. The first dimension of this array again corresponds to the number of examples that we're getting predictions for. So if we were passing in 2 examples in a stacked NumPy array, and so example now is an array where the first dimension is equal to 2, then we would get out a two-dimensional array where the first dimension is also equal to 2. As a final example, let's say our network is a multi-class classification model where there are 3 classes. So our final layer has 3 neurons and a softmax activation. And you'll see I've also changed the loss function from binary cross-entropy to categorical cross-entropy. I'm supposing that the number of input features is the same as before, 12. Let's also say that example again contains 2 data inputs, so that the first dimension of this array is equal to 2. Then the output of model.predict will look something like this. The array of output predictions will be a two-dimensional array as before. The first dimension will be 2, which matches the first dimension of example. That's the number of examples we're getting predictions for. And the second dimension will be 3, for the number of classes. Each row of this array is the network output for that data input. The output layer is a softmax layer, remember? So each layer is a set of output probabilities emitted by the softmax function. And you can see how they add up to 1 in each case. So here, it looks like the model is predicting class 1 for the first example and class 3 for the second. Now you've seen how to both evaluate our trained models as well as make predictions from them. In the final coding tutorial of this week, you'll apply this to the model you've trained on the Fashion MNIST dataset. So let's see how good its predictions are.
Welcome back. With Kevin, you have learned how to implement the evaluate and predict methods of Keras. Basically, with evaluate you can test how the neural network performs with the test dataset. And with predict, you can take new data as input to make predictions. Now it is your opportunity to put what you learned into practice. You are going to apply the evaluate and predict methods to the Fashion MNIST dataset, continuing what you did in the previous coding tutorials of the week. So let's see how we can do this. To begin, you can import the matplotlib and numpy packages. Then you are going to continue just after where you left it in the previous coding tutorial. Remember that you trained your model with the fit method for 8 epochs. Once you have trained the neural network, you can proceed to evaluate how it behaves with the test dataset. It seems that an error pops up with this code. The reason is the same as in the previous coding tutorials. You need to add a dummy channel dimension to the test dataset. As you see, from this you get some printout. Try using the verbose parameter as before. If you set verbose equal to 0, you won't get any output. And with verbose equal to 2, you will see the loss and the 2 matrix printed out. Now you can actually save those values of the loss function and 2 matrix by setting them equal to the evaluate method. I am defining the test loss, test accuracy, and test MAE variables for this. This is all for the evaluation stage. Now you can move on to the prediction stage, in which you can use your already trained and tested neural network to predict the class of a new image. For the sake of simplicity, here you will take as the new data just a particular image from the test dataset. I am providing you with a code that randomly chooses an image. However, I am going to slightly adapt it so that the image index is 30. This code shows the image and also its round truth label. It seems that the image represents a bug. Now let's introduce that image in the prediction method. As before, this gives us an error due to the dimensions. What happens is that the predict method expects a batch of images for the first dimension and the number of channels for the last dimension. Hence, you need to add a dummy dimension both at the beginning and at the end of test image. Finally, let's print the prediction on the screen to see if you have got it right. You can use np-argmax to get the class with the highest probability. I am defining a prediction variable with the results from model predict, and I will then apply the argmax function to predictions. Well, it seems that you have got the bug class right. There were some chances to fail, but luckily it has been fine. Nice work! So well done! Now you are able to use TensorFlow and Keras to train a neural network. You can also evaluate its performance and make predictions with it. In the assignment of this week, you will apply what you have learned to the MNIST dataset of handwritten digits. Now you can explore more the evaluate and predict methods. For instance, could you predict the labels of a batch of images simultaneously? This is my last coding tutorial, and it has been great exploring the amazing world of deep learning and TensorFlow with you. Bye bye and give your best in the assignment of this week. Hasta luego.
In this video, we'll see how to introduce validation sets into the training run. Validation sets are useful as a measure of how well our model is performing outside of the training set. So the model never uses the validation set to train on, but its performance is evaluated on the validation set during training. So here, I've built a simple feed-forward network. It's got a hidden layer with 128 neurons, with tanh activation, and linear output layer with 2 neurons. So this could be a regression model, where the target output is 2-dimensional. We're compiling the model with the Adam optimizer, a mean squared error loss, and we've chosen mean absolute percentage error as a performance metric. Just as a reminder from earlier, I'm creating the optimizer from the TensorFlow.keras.optimizers module so that I can change the learning rate for the Adam optimizer to 0.05. Now let's say that our dataset inputs are stacked into one big NumPy array, which here we're calling inputs. So remember, the first dimension of this array would be the number of examples in the training set, and the remaining dimensions would be for the features. Similarly, the first dimension of the NumPy array targets will be the same, number of samples in the dataset. The second dimension here should be equal to 2, as this needs to match up with the dimension of the output layer of our network. Let's say then that we want to track the performance of our model on a separate held-out validation set. One way we can do this is to pass in the validation split keyword argument. What this does is to automatically split the inputs and the targets into separate training and validation sets. The 0.2 you see here means that 20% of the data will be held back for validation. The model's performance is then recorded on both the training and validation sets. So you remember that the model.fit method returns a history object. Before, you saw how that history object records the training set loss and metrics over the course of the model training. Now this history object also records the performance on the validation set. You might also remember that these values were stored inside the history attribute of the history object, and this attribute is a Python dictionary. If we were to take a look at this dictionary, we'd see that it now not only has keys for the training set loss and metric values, but also for the validation loss and metric values. So then we can take a look at how our model performed on the validation set. Sometimes datasets have already been packaged up for us with the training and test split. You've seen this already before when you loaded the Fashion MNIST dataset with the tf.keras.datasets module. You could use this split as a ready-made training and validation split. So instead of getting the model.fit method to make the split for us, we explicitly give it the validation set. If we want to do that, then we can use the validation data keyword argument. This argument takes a tuple of inputs and outputs. As before, the model will then record the performance on this validation set during the training run. Finally, we might also want to make a training and validation split ourselves before feeding them to the model.fit method. For example, we could use the train test split function from sklearn to make a training and validation split, and then feed them into the fit method, again using the validation data keyword argument. So now we've seen how to include validation sets into our training run, using either the validation split keyword argument or the validation data keyword argument. This is a really important feature to build into our training workflow. In the first coding tutorial of this week, you'll put this into practice yourself on a simple dataset, so you can see how well the model performs on a held-out validation set.
Hi, I'm Melissa, and I'm a pure mathematics PhD student at Imperial College London. I'll be guiding you through this week's coding tutorials. This week, you'll see how to incorporate validation, regularization, and callbacks into a neural network using TensorFlow 2 and Keras. I encourage you to practice along with me so you're well equipped to tackle this week's programming assignment. In this coding tutorial, we'll be looking at validation sets. Let's get started. So now that I've opened my Jupyter notebook, I'll start by importing TensorFlow and confirm that I'm using TensorFlow 2. Throughout this week, I'll be working with the diabetes dataset from scikit-learn. I'll begin by loading the dataset. I first import it from the scikit-learn datasets library. I will now call the load diabetes function, which returns a dictionary containing all of the information about the dataset. Now let's print the description of the dataset, using the key DESCR in all caps. Right, so we can see that the dataset contains 442 examples. Each example consists of 10 attributes to be used as input to the model, for example, age and sex and body mass index, and the target for each example is a number representing the disease progression after 1 year. Now I will initialize our data and targets. First, I'll look at the keys of the diabetes dataset dictionary. You can see that the input data is stored as the value of the data key, and the targets can be found by using the target key. I'm now going to set our own variables to store the data and targets. So let's now look at our array of targets. You can see that they are all numbers varying roughly from 0 to 300. So before I continue, I'm also going to normalize my target data to make my training curves a bit clearer. So we take our array of targets, subtract the mean along the axis 0, and then we divide by the standard deviation. So let's have another quick look at our targets. Alright, so you can see here that the range is much smaller. Okay, so now that I have my data, I'm going to split it into test and training sets using the train test split function from scikit-learn. So I'm first going to import it from sklearn.model selection. Okay, great. And now I set my train data, train targets, and test targets to be equal to train test split I feed in my data and targets, and now I want the test size to be 10% of my total number of examples. So I'll put 0.1 there. Right, so now I'll just check the shape of the training data, the test data, the training targets, and the test targets. And you can see here that the number of test examples is 45, which is 10% of our total dataset size rounded up. Great. Now that I've read in and pre-processed my data, it's time to construct my feed-forward neural network model. So the first thing I'm going to do is perform some imports. So from TensorFlow.keras.models, I'll import the sequential model. And from TensorFlow.keras.layers, I'll import the dense layer. So now I'm going to define this getModel function, which will instantiate a model when I call it. And the model is going to be really quite simple. I'm going to have 6 dense layers, each with 128 neurons. All of the layers will have the same ReLU activation function. My output layer, of course, will only have 1 neuron, since our target is a single number. I'm also going to need to specify the input shape in the first dense layer, so that I can look at the model summary next. Rather than hard coding that there are 10 feature parameters, I will instead refer to the shape of the training data, in case I decide to modify the dataset later. Now here you should note that if I don't specify the input shape, then the weights will be created at the beginning of training, and I will not be able to view the model summary. So let me just continue to add my other dense layers here. So now I've just got to add my final dense layer with 1 neuron. And then I've just got to remember to return the model from my getModel function. I'm now going to call the getModel function to instantiate a model. Let's run this. Okay, great. And now I'll get the summary of the model. Okay, so here we can see the layout of our model, including the number of parameters we've got in each layer. And you can see that the total number of parameters we've got is 84,097. Okay, so let's now compile the model. So call model.compile. Now I'm going to set the optimizer to be the atom optimizer, the loss function to be the mean squared error, and as a metric I'll take the mean absolute error. So let's run this. Great. I'm now ready to fit the model to the data, so let's write history equals model.fit with our training data and targets. I'll train the model for 100 epochs, and I'll reserve 15% of the training examples for validation, so that we can compare model performance on the training and validation sets. My model will also have a batch size of 64, and I'll set verbose to false. Okay, my model is training for a few seconds here. Okay, so now that I've trained my model, I'll evaluate it on the test data. So I'll call model.evaluate. And you can see the loss here is 0.8778. Finally, let's plot the loss versus epochs graph on the training and validation sets. From the graph, we can see that the model has vastly overfit the training data, and so it underperforms on the validation data. In this coding tutorial, I have built a neural network model that overfits the scikit-learn diabetes training data. I encourage you to see if you can reduce overfitting by, for example, altering the number of epochs that the model trains for, or changing the layer structure of the model. In the next coding tutorial, I'll try to reduce the overfitting by introducing some regularization to my model. I'll see you then.
Welcome back. So we've now seen how to monitor the progress and performance of our model on a held-out validation set using two different keyword arguments in the model.fit method. Now we'll see how you can include regularization techniques into the model training that have the effect of constraining the model capacity and preventing overfitting. In particular, we're going to look at using L2 weight regularization, which is also known as weight decay in the context of neural networks, as well as L1 weight regularization. And you'll see how to include dropout in your models. Let's start with adding in weight decay to our model. Here we have a feed-forward network with a single hidden layer. This is a binary classification model. As you can see, the output has just one neuron and a sigmoid activation function. We can add in weight decay when we define our model. Dense layers, as well as convolutional layers, have an optional kernel regularizer keyword argument. To add in weight decay, or L2 regularization, we set the kernel regularizer argument equal to a tf.keras.regularizers.l2 object. This object is created with one required argument, which is the coefficient that multiplies the sum of squared weights in this layer. Remember that a dense layer has weights and biases, and the weight matrix is sometimes called the kernel. Here we've set the weight decay coefficient to be equal to 0.001. Once we've built the model together with the weight decay, we can compile and fit the model as normal. The weight decay penalty term is automatically added to the loss function when we compile the model. So here our loss function would be the binary cross entropy, calculated using the model predictions and the true labels, plus the sum of squared weights of the first layer of our model, multiplied by the weight decay coefficient of 0.001. This sum of squared weights term has the effect of penalizing large values of the weights, which encourages the model to find a simpler function that fits the data. This means the model is less likely to overfit to the training set. Instead of L2 regularization, we could use L1 regularization. In this case, the penalty term is a sum of absolute weight values instead of a sum of squared weight values. We can use L1 regularization in a very similar way. This time we're creating a tf.keras.regularizers.l1 object and passing that to the kernel regularizer argument. The regularization coefficient this time is 0.005. L1 regularization has the effect of sparsifying the network weights, or in other words, it results in some of those weights being set to 0. And in fact, there's no reason why you couldn't use both L1 and L2 regularization. Here we've created a tf.keras.regularizers.l1l2 object and passed that to the kernel regularizer argument. The coefficients for the regularizers can be set independently, so now the regularizer object has got two keyword arguments, one for the L1 regularization and one for the L2 regularization. In all of these examples so far, we've only been applying regularization to the weight matrix of the first dense layer. It's quite typical to only apply regularization to the weight matrix or the kernel of a dense or convolutional layer. However, it is perfectly possible to include regularization for the bias as well. Here we can see how to do just that. In the constructor of a dense or convolutional layer, there is also an optional bias regularizer argument. We can pass this argument, a regularizer object, in just the same way as we did before. And again, this will add a penalty term to the loss function, this time for the bias parameters. The final thing I'd like to show you is how to include dropout in your network. Dropout also has a regularizing effect in neural networks, and in TensorFlow we can include dropout as just another layer. So here you can see we're importing not only the dense layer as before, but also the dropout layer. Now in our sequential model, we've included the dropout layer in our list of layers. The dropout layer has a required argument, which is the dropout rate. Here the rate has been set to 0.5, and that means that each weight connection between these two dense layers is set to 0 with probability 0.5. This is sometimes referred to as Bernoulli dropout, since the weights are effectively being multiplied by a Bernoulli random variable. Each of the weights are randomly dropped out independently from one another, and dropout is also applied independently across each element in the batch at training time. Again, we can compile and fit our model as normal, with dropout layers included in our model. But remember that when we're using dropout, we typically have two different modes for how we run the network. At training time, we randomly drop out weights in the way that I've described, and we can think of this as training mode. However, when we're evaluating our model, or making predictions from it, we stop randomly dropping out the weights, and we can think of this as testing mode. These two modes are automatically handled behind the scenes by the model.fit, model.evaluate and model.predict methods. But it's worth bearing in mind that this is happening in the dropout layer, and later on we'll look at ways of getting more lower level control over the network, and you'll see then how these two modes of operation for dropout can be controlled. We're now starting to increase the sophistication of our models by including important concepts such as validation and regularization into our training workflow. You can also now include dropout as an additional layer, and later on in the week you'll see how to include batch normalization, also as an additional layer type. In the following coding tutorial, you'll implement regularization into your model and see for yourself firsthand how these techniques help your model to generalize beyond the training data.
Welcome back. Kevin has just shown you how to add regularization to your neural networks. In this coding tutorial, it's your turn to put this into practice. Let's open the coding tutorial notebook and get started. So first I'm going to import the dropout layer from tensorflow.keras.layers and the regularizers package from tensorflow.keras. I'm now going to write a function called getRegularizedModel. This function will return a sequential model similar to the one we saw previously, and in fact I have the same layer structure from the previous model already here. But this time I'll add L2 regularization and dropout layers. So this function takes a weight decay, WD, and a dropout rate as arguments. Let's add L2 regularization by including kernel regularizers in all but the final dense layer. We'll set each one equal to regularizers.L2 with the weight decay, WD, as an argument. Since the kernel regularizer is the same in each dense layer, I'm going to save some time by copying and pasting it. Now I add dropout layers between each pair of consecutive dense layers, where the inputs are dropped with the probability rate, the argument to our getRegularizedModel function, and the remaining inputs are scaled up by 1 over 1 minus the rate. Now if you're familiar with TensorFlow 1, you should be extra careful here when giving the dropout rate, because by default in TensorFlow 1, the argument is taken to be the keep probability, or 1 minus the dropout rate that we're using here. I'll now rebuild the model with my getRegularizedModel function, and I'll set the weight decay here to be 1 times 10 to the negative 5 and the dropout rate to be 0.3. Okay, so now that I've run that cell, I'll compile the model by calling model.compile. Again, I'll be using an atom optimizer, mean squared error loss function, and as a metric I'll take the mean absolute error. So let's now train the model and see how its performance compares to the unregularized version. So I'll call model.fit with the same hyperparameters as before. So in particular, I'll run training for 100 epochs. I'll have a 15% validation split and a batch size of 64. And for convenience sake, I'll just set verbose to false again. So now our model's running. Okay, so now I'm going to evaluate the performance of the model on the test data. So you can see here that the loss is much smaller when compared to the unregularized model. Finally, let's plot the learning curves for the training and validation sets. Here you can see that the overfitting is not completely fixed, but there is a significant improvement when we compare it to the unregularized model. In this coding tutorial, I have used L2 regularization and dropout to reduce overfitting of a neural network model. I encourage you to try this for yourself and play around with different regularization techniques and parameters to see if you can increase the regularization effect. In the next coding tutorial, I'll be showing you how to use callbacks to monitor your neural network models. I look forward to seeing you then.
Welcome back. You now know how to include a validation set in your training in order to monitor the performance of your model on data that isn't used for training. You've also seen how to include regularization into your model to help avoid overfitting and improve the performance of the model on the validation set. You've implemented extra weight regularization penalty terms that are added to the loss function and added dropout into the network. But even though we're monitoring the performance of our model on the validation set, we're still having to fix the number of epochs that the model is training for ahead of time. What we'd like to do is to have the ability to not only monitor the performance of the network, but also perform certain actions depending on those performance measures. That's where callbacks come in. Callbacks are an important type of object in TensorFlow and Keras that are designed to be able to monitor the loss and metrics at certain points in the training run and perform some action that might depend on those loss and metric values. Let's take a look at how callbacks are constructed. In TensorFlow, all callbacks are stored in the tensorflow.keras.callbacks module. Inside that module, there's a base class called callback, which all other callbacks inherit from. You can also subclass the callback base class yourself to create your own callbacks, and that's what we're going to start to look at first, as this is a really nice way to get a feel for how these objects work. Here, I'm creating a new class called myCallback, and you can see that I'm subclassing the callback base class. This base class has a series of methods that can be overridden in our new class definition. These methods will then be called at different points in the training. For example, one of the methods of the callback base class is called onTrainBegin. This method optionally uses the logs keyword argument, and you'll find out more about that in a notebook reading coming up in this week. For now though, you just need to know that, as the name suggests, this method will be called once at the start of training. So we can override this method in our new callback to perform some action at the beginning of the training run. Similarly, there are more methods of the base class that are called at other points in the training. You can pretty much just read it from the name. onTrainBatchBegin is called at the start of every batch or every iteration of the training. You can see that this method has a batch argument. So when this method is called, the batch number will be passed in using this argument. So if you want, you can use the batch number during training to perform some action within this method. You'll see an example of this in the next coding tutorial. The train part of onTrainBegin and onTrainBatchBegin means that these methods will only be used in the training run. We can actually also use callbacks in evaluation and prediction runs as well, and again you'll see examples of this in the following coding tutorial. OnEpochEnd is the method that's called at the end of every epoch. This method has an epoch argument, so similar to before, when this method is called it gets passed the epoch number, so we could use this number within the method if we want to. Once we've defined the actions we want our callback to take at these various parts of the training run, all we need to do is to pass in the callback to model.fit. Model.fit has a callbacks keyword argument, and this takes a list of callback objects. So here we're passing in an instance of our callback. Remember again that model.fit returns a history object. So by this point it should make sense that this object is actually an example of a callback. It's a callback that is automatically included into every training run whenever we call model.fit. The action that this callback takes is simply to record the loss and metric values and store them as a dictionary in its history attribute. There are quite a few built-in callbacks in TensorFlow, and we're going to be covering several of them in this and later weeks of the course. But you can take a look at the list of built-in callbacks if you go to the API documentation on tensorflow.org. So here's the tf.keras module, and inside there is the callbacks module. And here's the list of built-in callbacks, and a couple of these names you'll recognize already. Here's the base callback class that we can subclass to create our own callbacks. And here's the history callback that I was just talking about that's automatically added into every training run. If we just take a look at the callback class, on the right hand side here you can see the list of methods that you can override when you create your own callback that are called at different parts of a training, evaluation or prediction run. And the names are quite self-explanatory, so down the bottom here you can see 4 methods with the word train in the name, and these methods would be called when you run model.fit. These 4 with test in the name would be called by model.evaluate, and these 4 with predict in the name would be called by model.predict. So now you know the purpose of callbacks and have a rough idea of how they're used. In the following coding tutorial, you'll consolidate this by putting it into practice and creating custom callbacks to perform certain actions. For now, these actions will be simple and just serve to demonstrate how to use callbacks, but we'll soon be using callbacks for several important aspects of our model training.
Hello, it's nice to see you again. In this coding tutorial, I'll show you how to implement custom callbacks to monitor your neural network models. So let's open the coding tutorial notebook and get going. So here I am back in my Jupyter notebook. The first thing I'm going to do is import the callback class from tensorflow.keras.callbacks. Now I'm going to define a simple custom callback that will print feedback at various points during training. This callback will be a child class of the callback class that I just imported. The onTrainBegin function can be used to give information at the start of training. In addition to the self argument, this function also takes the logs argument that I will set to none by default. So here I'm just going to print starting training. The onEpochBegin function, as it sounds, runs at the beginning of every epoch. Here notice that the function has the additional epoch argument, which you can of course call in the function, which is what I will do with my print statement. The onTrainBatchBegin function will run at the start of every training batch. Here, there is also the batch argument, and I will print that as we are starting each batch. The onTrainBatchEnd function, of course, runs at the end of every training batch. It takes the same arguments as its beginning counterpart. Next, I'll use the onEpochEnd function to print a message at the end of every epoch. As you might expect, this function has the epoch argument like its beginning counterpart. And finally, the onTrainEnd function runs at the end of training. Now keep in mind that when you are writing your custom training callback, you can use as many or as few of these functions as you like. Now that I've run this cell, I'll rebuild my regularized model. I'll again set my weight decay to 1 times 10 to the negative 5 and my dropout rate to 0.3. I'll compile my model now, using the Adam optimizer and mean squared error loss as usual, but this time I'll omit the mean absolute error. And now I'll run the fit function. I'm only going to run it for 3 epochs this time, so that we're not overloaded with printed messages. I'll also double the batch size and turn off the messages from the fit function, since enough information will be given by my callback. I can use my training callback in the model with the optional callbacks keyword argument. Now you can see that my callback has given all of the feedback expected. You can also define custom callbacks to complete tasks during evaluation and prediction. Let's now see an example of a testing callback. In the same way as we define functions for the training callback, you can also define functions onTestBegin, onTestBatchBegin, onTestBatchEnd, and onTestEnd. Notice that there are no epochs used in testing, so there are no corresponding functions there. All of these functions take the same arguments as their training counterparts. So as you can see, I'll construct my testing callback by simply editing my existing training callback. As with the training callback, you can implement the testing callback by simply using the optional argument callbacks in model.evaluate. And you can see that the testing callback works as we expect. Finally, I'm going to define a prediction callback that will run when we call model.predict. Again, the available functions are onPredictBegin, onPredictBatchBegin, onPredictBatchEnd, and onPredictEnd. So again, I'll just edit this testing callback since the functions take the same arguments as their training and testing counterparts. I'll end this tutorial by now running model.predict with my prediction callback. And here we see all of the feedback from our prediction callback. So in this coding tutorial, you've had some practice defining custom callbacks to monitor your models during training, testing, and prediction. I encourage you to come back to this notebook after you've completed the logs dictionary reading to see if you can adapt the callbacks we've written to give information about the values of metrics or the loss function. Next, Kevin will show you how to implement the early stopping callback, and I'll be back to work through an example in the next coding tutorial. I hope you'll join me then.
We've seen how to include validation sets and regularization techniques into our model training, and we took a first look at callbacks. In this video, we'll use a callback to implement another regularization approach called early stopping. Early stopping is a technique that monitors the performance of the network for every epoch on a held-out validation set during the training run, and terminates the training conditional on the validation performance. The Keras module contains a built-in callback designed for this purpose, called the early stopping callback. Let's see how it works. In this example, I've built a convolutional network, starting with a conv 1D layer, followed by a max pooling 1D layer. Note that the input is two-dimensional, so this could be a univariate time series of length 128, for example. Then we flatten the input by unrolling into one long vector. And finally, we have a dense layer with a 10-way softmax. We're compiling the model with the Adam optimizer, categorical cross-entropy loss, and we're tracking the categorical accuracy metric. Okay, so here's where the callback comes in. At the top, you can see that I'm importing the early stopping callback from the TensorFlow.keras.callbacks module. And in this line, I'm creating an early stopping callback object. This callback has a few options that we'll look at in a moment, but for this instance, we're using the defaults. Then we just need to pass in the callback to the model.fit method. Here you'll see we're passing this callback in a list to the callback's keyword argument. It's a list because in practice you might be passing in a number of callbacks, all of which are performing different tasks during the training run. So what the early stopping callback is doing is monitoring the performance of the network on the validation set, which you'll see we've created here with the validation split keyword argument, and it stops the training depending on how that performance progresses. So a natural question is, which measure of performance is the callback monitoring? The early stopping callback constructor takes a keyword argument called monitor, which can be used to set which performance metric to use. You can see here that I've passed in val loss for this keyword argument to say that I want to use the validation loss as the performance measure to decide when to terminate the training. And this is actually the default setting for the early stopping callback. In this model, the loss is the categorical cross-entropy loss. As an example, you can instead choose to use the validation accuracy as the performance measure to decide when to terminate the training. Remember that we said to track the accuracy metric when we compiled the model. If we had more metrics that we'd used when we compiled the model, then we could have used one of them instead. By the way, the actual string name that you see being passed into the monitor argument here is the same as the string that's used as one of the keys in the history object that's returned from model.fit. So that's one way that you can check what string you should be using here. Another keyword argument that we can set in the early stopping callback is the patience argument. By default, patience is set to 0, and that means that as soon as the performance measure gets worse from one epoch to the next, then the training is terminated. Now this might not be ideal since of course the model's performance is noisy and it might go up or down from one epoch to the next. What we really care about is that the general trend should be improving. That's why we'll often set the patience to some number of epochs, like here I've set it to 5 epochs. In this case, the training will terminate only if there is no improvement in the monitored performance measure for 5 epochs in a row. The early stopping callback also has a min-delta argument. This option can be used to define what qualifies as an improvement in the monitored performance measure. For example, if I set here the min-delta to be equal to 0.01, that means that the validation accuracy has to improve by at least 0.01 for it to count as an improvement. If the validation accuracy improved by a smaller amount, say by 0.001, then that would be treated the same as a worsening of the performance by the early stopping callback, and the patience counter would increase by 1. By default, min delta is 0, which means that any improvement in the performance is enough to reset the patience. The last thing I want to show you is one more option that we can use in the early stopping callback, and that is the mode keyword argument. You might have noticed that depending on the choice of quantity that we're monitoring, an improvement could be either an increase or a decrease in that quantity. If we're monitoring the validation loss, then we want the loss to go down, but if we're monitoring the validation accuracy, then we'd want that to go up. How does the early stopping callback know which direction is better? Well, by default, the mode keyword argument is set to auto, which means that the direction is automatically inferred by the quantity name. If you're tracking the loss or the accuracy, then the callback knows what this is and whether increasing or decreasing is better. However, you can explicitly set the direction in the early stopping callback. For example, here I'm setting the mode to be max, which means that we're aiming to maximize the monitored performance measure, which is the validation accuracy. In this lecture video, we've looked at an example of how callbacks are really useful objects to incorporate into our model training. There's more that you can do with callbacks, of course, and you'll see more examples of that in this week and later on in the course. For now though, you're ready to go through the final coding tutorial of the week and implement early stopping into your training.
Hi, and welcome back. In this session, I'll be showing you how to implement early stopping and patience into your neural network models. Let's jump in. So you should hopefully now have opened your Jupyter notebook, and the first thing we're going to do is add early stopping to an unregularized model. First, I'll instantiate the model by calling the getModel function that I defined previously, and then I'll compile it with the Atom optimizer and mean squared error as my loss function. So let me do that now. I'll now fit my model to the training data. I'll split the arguments of the fit function over several lines so we can see them all clearly. I'll run the training for 100 epochs with a validation split of 15% and a batch size of 64. Let's also again set verbose to false. This time, let's also include the early stopping callback, found in tf.keras.callbacks. Okay, so now that's done, I'll evaluate my model on the test data. And you can see here that the loss is 0.5242. Now I'm going to repeat this process with a regularized model so I can compare their performance. Again, I'll start by instantiating my regularized model by calling the getRegularizedModel function that I wrote previously. I'll set the weight decay to 1 times 10 to the negative 8 and the dropout rate to 0.2. I'll now compile the model and train it in the same way as the unregularized version. So again, I've got the Atom optimizer and the mean squared error loss function. So now when we fit the model to the training data, I'll again split the arguments of the fit function over several lines for easy reading. So again, we'll have 100 epochs. The validation split will be 0.15. The batch size will be 64. I'll set verbose to false, and we'll also use the early stopping callback. Okay, great. I'll now evaluate the regularized model. You can see here that the loss is 0.5305, so this is actually a little bit worse than our unregularized model. Let's plot the learning curves of the two models using this function I prepared earlier. You can see that in both cases, the fit function has run for 3 epochs before early stopping has kicked in. I'm now going to implement patience into the early stopping callback as an optional argument. I'll start by setting the patience to 10 for both models. I'll now regenerate the learning curves. We can see here that this is perhaps too much patience because there is already overfitting, especially for the regularized model. So I'm going to reduce my patience now to 2 epochs. So let's go and do that. Let's finally replot. Okay, so that's better. You should note that there is the potential for wide variability in the results of training these models, since, for example, your weights will be initialized differently to mine, so don't worry if your plots look a little bit different. I also encourage you to play around with these models and use some of the callbacks included in the additional callbacks reading later this week to get some more experience. In this week's coding tutorials, I've shown you how to split off a validation set from your training set and use it to assess the performance of your model. You've also got some experience implementing regularization techniques to improve your model's performance, and also using callbacks to monitor your model and to add to regularization effects. Thank you for joining me for these coding tutorials, and good luck in the programming assignment.
Welcome back. In this lecture video, we're going to take a look at saving TensorFlow model parameters and loading them from previously saved files. We'll see how to save model weights automatically during a training run, and for this we'll use a built-in callback called the model checkpoint callback. It's also possible to manually save the weights of a model, for example after a training run has completed, so you'll also see how to do this. An extra detail is that there are 2 different formats available for saving and loading files, due to there being a native TensorFlow format, as well as the HDF5 format used by Keras. For the moment, we're just going to be saving model weights only. We'll cover saving the weights and architecture later on in the week. So here's an example of how to save a model during a training run. As I mentioned, we're using a built-in callback here called the model checkpoint callback. These first few lines should be pretty familiar by now. You can see that I'm building a simple feed-forward network using 2 dense layers. The output is a single neuron with a linear activation. Here's a reminder of something you learned previously. I'm compiling the model using the stochastic gradient descent optimizer, and for the loss function I've instantiated a binary cross-entropy object and fed in the argument from logits equals true. The binary cross-entropy class is imported up here from the tensorflow.keras.losses module. So this network is actually a binary classifier, and the linear unit output will be squeezed through a sigmoid activation function that is being handled by the loss function itself. We're importing the model checkpoint callback from the tensorflow.keras.callbacks module, and down here we're creating a model checkpoint object, which I'm calling checkpoint. The constructor of this callback has one required argument, which is the file path. This is the name the callback will use to save the model. You can see we're also using another keyword argument here. I've set save weights only to be true. As you might have guessed, this means that only the model weights will be saved by this callback, and not the architecture. The final line should again look familiar. We're calling model.fit, passing in the training inputs and outputs, and setting it to train for 10 epochs. Just as we did previously, here we're using the callback's keyword argument and passing in a list, which contains our model checkpoint callback object. This callback will save the model weights after every epoch. Now, because we're using the same file name to save the model, the saved weights will get overwritten every epoch. We'll see how we can change that later on in the week. But what you'll see after the weights have been saved is that there are 3 files created in the current working directory. These are the files that contain the model parameters. And you can see here that the first part of these file names is my model, which is the file name we specified in the callback constructor. There's also an alternative format that you can use to save the model weights. The format used by Keras is the HDF5 format. These file formats often use the extension .h5. If you give the file path argument the h5 extension, like I've done here, then the model will save the weights in the Keras HDF5 format. And what you'll see after running the training is that the model weights will have saved to a single HDF5 file in the current working directory. For most models, it doesn't really make a difference which format you use, but in general, I'd recommend using the native TensorFlow format. Okay, so we've saved the model weights during a training run. How do we load weights that have been previously saved? So remember that we've only saved the weights and not the model architecture. And that means to use the saved weights, we still have to have the code to rebuild the model. So here is the same code that we used before to define this model. And let's say we've just built this model again from scratch, so the weights have been randomly initialized. We can then load the weights we've saved from a previous training run by calling model.loadWeights and passing in the same file name that we used to save the weights. If we had saved the model weights in the HDF5 format, it's exactly the same. Just pass in the file name together with the h5 extension. The final thing I'd like to show you is how to save the model weights manually, that is, without using the model checkpoint callback. So for example, let's say we've built and compiled our model, like we can see here, and maybe we've used an early stopping callback, which you already know about from earlier. You can see in this line I've created the early stopping callback object, and just as a reminder, notice that it's monitoring the mean absolute error metric on the validation set, and the patience is set to 2. That means that the training will be terminated if the validation mean absolute error performance doesn't improve after 2 successive epochs. Okay, so in this line we're launching the training. And again, as a reminder, you can see that I've passed in the training inputs and targets and created a validation set by holding back 20% of the data. And the maximum number of epochs that this model will train for is 50. And here I'm passing in the early stopping callback. So depending on how the training progresses, the model might reach an optimal performance on the validation metric and the training is terminated. We can then manually save the model weights like this, just by calling model.saveWeights and again passing in the file path that should be used to save the weights. So now you've seen how easy it is to save the parameters of your model, either using a callback during the training run, or manually by using the model.saveWeights method. You can also load the weights that you've previously saved, assuming that you have the code to build the same model architecture that the weights were saved from. In the next lecture video, we'll take a look at some of the options that are available when saving models during a training run using the model checkpoint callback. But first, it's time to code some examples yourself. In this week, Adrian is going to be walking you through the coding tutorial notebook. So have fun with that, and I'll see you in the next lecture video.
My name's Adrian, and I'm a PhD student at Imperial College in London. This week, I'll be guiding you through some coding tutorials. They'll be on this week's topic, which is saving and loading models. Let's get straight into it. In the last video, Kevin showed you some of the ways in which you can save a TensorFlow model during training and reload it back for later use. In this tutorial, you'll be doing this yourself in your own notebook. Let's fire up this notebook and get straight into it. Once we've fired up this notebook, let's go and import TensorFlow. It should give us version 2.0.0, which it does. And in this session today, you'll be using the CFAR10 dataset. It's quite a standard machine learning image classification dataset, and it's got 60,000 color images in total, with one of 10 labels each. So you can see the 10 labels here, as well as a link with some more information. And since it's so standard, you can actually import it directly from Keras. So I've provided the code for you to do that right now. And I've actually given you a slightly smaller subset, so just the first 10,000 training images and the first 1,000 test images. This is just to speed training and evaluation up a little bit. So in your own time, you could do it with the full data set if you like. The idea will be the same, but this just speeds things up a little bit. So let's go ahead and run this cell to actually import the data set. Now, the first time you do this, you might get a print statement that says it's downloading, but it's already on my machine, so you won't get it the second time. And what I've also done is I've provided some code for you, which plots the first 10 CFAR10 images. So this is just to get a feel for the data set. So let's actually run this. You might run the cell twice to encourage the notebook to actually give you the output, but now you see what we're working with. So fairly small color images in one of 10 categories. You see a truck, a frog, a horse, a ship. You kind of get the idea. And we're trying to build a neural network today which classifies these 10 images. What I've also provided for you are two useful functions. So the first is called getTestAccuracy. What this does is it takes a model and some testing data and it just spits out the classification accuracy. And I've also got a function called getNewModel, and you'll see why this is useful in a second. But what it does is it creates a new instance of a simple convolutional neural network. You can see the layers here, and I've also imported, see it's got dense, flatten, some convolution, and some max pooling layers. And it also compiles it, but it doesn't train it. So it just creates a new kind of initialized instance of a sequential convolutional neural network. So let's go ahead and define that. And let's use this function right away to actually create a new model. So let's write models get new model like this. And let's actually print model.summary. So let's see what kind of model we're working with here. You can see the type of net this is. So it's a convolutional neural network. It's got two convolutional layers, a max pooling layer, and then flattens everything, and then two dense layers, where the last layer's got 10 outputs, and it's a soft max. So this is how you are actually classifying these things. And let's also get the test accuracy of this model. So if I write get test accuracy of model X test and Y test like this, well, it's untrained. We've got 10 possible classification. You'd expect it to kind of get around 10% accuracy, right? As good as random guessing. And you see that's actually the case. So 10.2, just a little bit higher, but yeah, roughly 10% accuracy. By the way, the number you get for the test accuracy will be slightly different, right? So I get 10.2%, but you might get a slightly different value due to a different initialization of this network, but it should be kind of around 10%. So now let's go ahead and train this model. Now, as Kevin mentioned, one of the ways in which you can save TensorFlow models is via model checkpoints, which are essentially snapshots of the model taken during training. Let's go ahead and create one of these things. So we'll first need to import this model checkpoint. So from TensorFlow Keras callbacks, import model checkpoint. Let's go ahead and do that. And let's go ahead and create one of these checkpoints. So I'll write first checkpoint path. So this is going to be model checkpoints and then checkpoint. So what this does is it creates a directory called model checkpoints and then a file called checkpoint inside it. And let's go ahead and create the actual checkpoint now. So I'll do checkpoint is model checkpoint. This is the thing I just imported. I'll let file path is going to be checkpoint. Checkpoint path. That should be a comma. Checkpoint path. Frequency. So I want to save every epoch. So at the end of every epoch during training, I'm going to save this thing. Let's save just the weight. So I'll write save weight only is true. So I don't save the model architecture. Let's put verbose equals 1 so we get some sort of print statements. And what I'd also like to mention is that, well, this model checkpoint is the same file every time. So at the end of every epoch, it's going to overwrite the same file name. Let's go ahead and actually use this thing. And the way we use it is we call this checkpoint as a callback in our model.fit. So model.fit, as I'm sure you're familiar with now, X is going to be X train like this. Y is Y train. Let's see, epochs is 3, so we're going to train for 3 epochs. And let's import this checkpoint as one of the callbacks. All right, checkpoint here. Let's go ahead and see what happens. So we're going to run this model.fit now. Oops, I forgot to actually run the cell, and let's go and run this thing now. So see it's training. Well, it's taking a little while, so what I might do is I might fast forward and meet you guys at the opposite end of this training session. Okay, my model is now finished training. So let's see what the print statements were. So we've gotten these normal epoch statements, the training statements that you're used to seeing. And I also got this new statement, which is saving model to model checkpoint / checkpoint. So what you see here is that at the end of every epoch, it saves the model in the directory model checkpoints to a file called checkpoint. And it does this every epoch, right? So at the end of every epoch, we overwrite the same checkpoint file. Let's have a look at what files were actually created here. So what I can do is if I use an exclamation mark, I can run Unix commands from a notebook. So if I do ls/lh, what this does is it lists the directory, and this -lh means that it gives us a little bit more information about the files and also in human readable format. So I'll do that with model checkpoints. So what this does is it lists the contents of the directory model checkpoints. Let's go ahead and run this and see what's being created. So you see 3 files here. We have checkpoint.data 0.001, and checkpoint.index. And you'll learn later what these files actually are, but for the moment, all you really need to know is that this checkpoint.data, which is by far the biggest file, 174 kilobytes for me, this is where the actual weights are stored. And the other things are a little bit of metadata. Now let's go ahead and also, let's get the test accuracy for this trained model. So I'll do get test accuracy of model again, x test, and y test. And let's see what it gives me. So it gives me 47%, so just less than half. I mean, we only trained it for a very small time. And by the way, this value, just like the value you had before, it'll probably differ for you, right? So it'll probably be kind of close, but obviously since you had some slightly different initializations, the value is going to differ a little bit for you. I mentioned that this checkpoint saves the weights. So if we create a new model, let's see if we can load these weights back onto it. So what I'll do is I'll create a new model like this. So I'll do models get new model. And then let's get the test accuracy for this thing as well. So let's get test accuracy of model, x test, and y test. Now this is going to be newly initialized. So you expect this to kind of have roughly 10% essentially guessing accuracy at the moment. So yeah, a little bit less than 10%, but around 10%. Again, this value might differ for you, but it should be around 10%. And how do we load these weights back on? Well, we can use the inbuilt model.load weights, this thing here. So I'll do model.load weights. All right, checkpoint path. This is the thing I defined earlier. Let's get the test accuracy. Let me scroll down a bit. Let me just get the test accuracy for this new model. And this should be the same value you had before. So for me, it should be 47.7%. For you, it'll differ a little bit, but it should be the same number as the one up here. Of course, the fact that this model has the same testing accuracy as the old one isn't really a proof that it has the same weights. But if you want to verify this for yourself, you can go ahead and check that they really do have the same weights. You really are loading on the same weights. Now I've given you just one more piece of code, which is another Unix command. And what this does is it just clears the model checkpoints directory. And the reason you might want to do this is that if you want to continue with this and kind of mess around with this code yourself, it might be good to delete the directory with the checkpoints that we just created together, so that if you create your own checkpoints, they don't get mixed up with these ones essentially. So if you want to run that cell, all it does is it cleans up your workspace a little bit so you can kind of tinker around with the stuff yourself. So you've just seen how to use model checkpoints, which are just one of the ways TensorFlow allows you to save a model. You can imagine this is especially useful during training. You can save models and continue training later, or just ensure you haven't lost work if things cut out. It's your turn to explore this functionality a little bit more. Try, for example, to design a script that loads a checkpoint and continues training. Or can you design and save different model architectures than the one I gave you to try and beat my classifier? In the next few coding tutorials, you'll learn about ways to customize checkpoints and other ways to save models. See you then.
So now you've seen how to use the model checkpoint callback to save your model every epoch during a training run. But you might want to have more flexibility when it comes to saving your model. For example, you might want to save your model with a different frequency or according to some criteria. The model checkpoint callback comes with a few extra options that help you to do this. So let's take a look at what they are. So this time we have a model with 2 dense layers and a dropout layer with dropout rate of 0.3. The output layer is a three-way softmax, so this looks like a classification model with three classes. We're compiling the model with the RMS prop optimizer, and we can see from the loss function that the target data is in sparse form, or in other words, each target value is an integer equal to 0, 1 or 2. We're tracking two metrics, the categorical accuracy and the mean absolute error. And here's our model checkpoint callback. This time the file path points to the folder training run 1, which will be created if it doesn't exist, and inside that the name used to save the model is my model. Again, we're saving weights only. The final line here is just training the model for 10 epochs using a batch size of 16 and passing in the checkpoint callback. As we've seen, the model checkpoint callback will save the weights at the end of every epoch by default. Here's a new keyword argument that can be used when you create the callback. This argument sets the save frequency, and the default value is the string epoch, which is shown here. But you can instead set this argument to an integer value, and this sets the frequency of saving in terms of the number of samples that have been seen by the model since the last time the weights were saved. So just to emphasize that point, the save frequency argument specifies the number of samples and not the number of training iterations. So here, my model would save the weights every 1000 samples, and I have a batch size of 16, and that means that my model would save every 62 or 63 iterations. Here's another option you can pass into the callback constructor. The keyword argument save best only defaults to false, but if you set it to be true, as I've done here, then the model will only save the weights according to a performance measure criterion. That criterion is set by the monitor keyword argument. The default value of this argument is val loss, which I've shown here. In this case, the callback only saves the weights if the validation loss is the best value seen so far in the training run. This looks quite similar to what we saw before with the early stopping callback. The callback behaves in a certain way according to how the training is progressing. Just in the same way as we've seen with the early stopping callback, you can choose which performance measure the callback is monitoring. Here I've changed the monitored performance measure to be the validation accuracy, which is one of the metrics I added when I compiled the model. This should also look familiar. A related keyword argument is mode, and again, as before, this argument tells the callback whether we're trying to maximize or minimize the monitored performance measure. Here we're monitoring the validation accuracy, which we want to maximize, so mode is set to max. The default for mode is auto, which will automatically infer from the name of the performance measure which direction we want it to go in. One more thing I'd like to show you is that the file name itself can be formatted with whatever keys are available in the logs dictionary. So for example, if we're saving the model every 1000 samples, we could make the file name include the epoch and batch number. If we do this, then no saved files would be overwritten, as they would all get a unique file name. Here's another example of that. In this case, we're saving the model every epoch, so we're including the epoch number in the file name, and we could also add the validation loss into the file name as well. So you can now save your network model during a training run with more flexible options. Just as we saw with model validation, callbacks are again really useful objects to dynamically perform actions according to certain criteria. Here, the model checkpoint callback can be set to only save your model if its performance during the training has improved. In the next coding tutorial, you'll put this into practice to see how this works for yourself. After that, we'll be taking a look at saving and loading the entire model, including the architecture as well as the weights. So I'll see you then.
Welcome back. With Kevin, you learned how to customize checkpoints to, for example, save at custom frequencies or save only the weights that generated the highest validation accuracy. In this coding tutorial, you put these ideas into practice. Let's open up the notebook now and get started. Notice this is the same notebook we were using before, so let's go ahead and import TensorFlow. Today, you'll be working through model saving criteria, this part 2, and you'll be using the same dataset you used last time. So we're going to be using the CFAR10 dataset again. So let's go ahead and rerun this cell this one over here. So we import the C410 data set again. I'll just rerun it like that. Let's run these two cells as well. So so we can use this function get test accuracy and get new models. We're using the same model and the same data set today. And let's go ahead and scroll down to model saving criteria down here. So let's start by creating a checkpoint. So let's run this import model checkpoint cell again. We're going to create a checkpoint here, but with a little bit more customization. So what I'm going to do here is I'm going to create a checkpoint that saves the model weights every 5,000 training points. And TensorFlow has this neat trick where you can format the checkpoint path using the epoch and batch. You can actually also use the validation accuracy and the validation loss. Let's just stick with the epoch and batch for now. So let's see how this works. All right, checkpoint 5,000 path. And the reason I call it checkpoint 5,000 is because I want to save every 5,000 training points. And I'll call it model checkpoints, right? So I'll create a directory called model checkpoints 5,000. And then I'll write checkpoint. And what I can do is I could put epoch like this. This is epoch with 2 digits. And then I also do the batch in the same way, like this. So what this does is it saves every 5,000 training points, and then in the file name, it has the epoch and batch, which means that before we were overwriting the weights every time. And this time we're not going to do that. They're all going to have different names. Let's go ahead and actually define the checkpoint. So I'll write checkpoint is 5,000 is, no, I just do model checkpoint like this. And then I'll write file path is checkpoint 5,000 path like this. Let's save the weights only. So alright, save weights only is true. So we're still saving only the weights. Now, instead of writing save frequencies epoch, which I had before, I'll write 5,000. So every 5,000 training points it saves. Let's put it for verbose equals 1 so we have some print statements that we can work with again. So I've created this checkpoint now. And now I play the same game. So I'll just fit the model with this checkpoint. So first let's do models get new model, right? So I've created a new instance of an initialized and untrained model. Now let's go ahead and do model.fit as you saw before. And I'll do x is x train, y is y train like this. Let's train it for 3 epochs again. Let's give it some validation data as well this time. So let's see what, like this. Let's make the batch size 10. And you'll see why I'm doing this later, but I'm going to want the batch size to effectively divide the save frequency. And you'll see why this is like this in a sec. And then I just put the checkpoint 5,000 as a callback. So let's go ahead and do this. Let's go ahead and run this thing. Okay, so it's training. Now again, this might take a little while. So I'll meet you on the opposite end of this training session. So my model's now finished training. Let's have a look at the print statements. So what happened here is, well, after 5,000 training points are pretty close to it, I said saving model to model checkpoints 5,000, and then checkpoint 01. The 01 refers to the epoch, so it's the first epoch, and the 499th, essentially the 500 batch. And that's why I chose this batch size as 10. So 5,000 training points corresponds to 500 batches. So you can kind of see what's going on here. So every epoch, I had 2 model checkpoints saved. The checkpoint 01499 is after the 500th batch and after the 1,000th batch, essentially the end of the epoch, since every training data set has 10,000, our training data sets have 10,000 images, and does the same thing for epochs 2 and 3. And notice now that the file name has changed. So this file name is different than that one, for instance. So before we were overwriting our weights every time, but now we're actually creating new ones. Let's have a look at what's actually in this directory. So I can use the same, let's do ls, lh, and I'll type model checkpoints 5,000. So let's see what's actually in this directory right now. So you see, it's a lot more files than last time. So we've still just got one checkpoint. This is a sort of metadata. But now, every time we save the checkpoint, it got a different name, so we have different files. So you see here the weights for the first epoch, the 500th batch, and here's some metadata about those weights. You see it keeps going like that. Now what we can also do is we can work with model saving criteria. So you'll probably recognize this from an earlier lecture. So what I'll do here is I'll create a tiny training and test set, so just 100 pictures in each. And what's going to happen now is we're going to create a model, but there's only 100 training samples, so it's going to overfit. And what we're going to do is we're going to create a checkpoint that only saves the model weights that had the highest testing or validation accuracy. So you might say, well, after a while, I'm overfitting on a training set, so you'd expect my validation accuracy to kind of plateau or not go up anymore. So let's see if we can just basically find the point at which it starts overfitting and use just those weights. So let's go ahead and create a new instance of this model. So let's do get new model like this. Let's go ahead and run this thing. Oh, I forgot to run this cell, so don't forget to run this cell. Here we do, models get new model like that. Now let's create a TensorFlow checkpoint, which only saves the weights that have the highest validation accuracy. So I'll write checkpoint best paths, right? By best I mean the best validation accuracy. So I'll do model checkpoints best, and I'll call this one checkpoint again. So I've created a directory called model checkpoints best. And then let's go ahead and create this checkpoint now. So I'll do checkpoint best is, well, model checkpoint, like you're familiar with. I'll do file path is checkpoint best path like this. Let's save just the weights. So save weights only is true. Let's go back to epoch here. So I'll do save frequency as epoch. Let's use the monitor is what TensorFlow uses to decide whether to save the weights or not. So let's do monitor validation accuracy. And now let's do save best only is true. So it only saves the weights with the highest value of the monitor. In this case, it's the validation accuracy. Let's do verbose equals 1. So I've created this checkpoint now. Now let's go ahead and actually train this model. And we'd expect some sort of overfitting. So what I'll do is I'll write history equals. What this does is it means it saves essentially the training and testing curves. So I'll do x is x train like this. Y is y train like you're used to. Let's train for 50 epochs. It's quite a long time. Now let's use the validation data. So it gives us some sort of validation outputs as well. We need this for the monitor. Let's make the batch size as being equal to 10 again. And then let's put this checkpoint as a callback, so checkpoint best. I'm actually going to turn verbose down to 0 now because we're training for 50 epochs, so otherwise I'm going to get a little bit too many print statements. Let's go ahead and run this thing and see what happens. So you see here, it's every epoch. It's only 100 training samples every epoch, so it's going pretty quickly. You see, when the validation accuracy improves, it goes up essentially. It saves. So if it goes up, let's say it went from 7% to 10%, saving model to model checkpoints best. But when it doesn't improve, it doesn't do anything. And also, I'm using the same file name again every time. So it's going to overwrite this file. So at the end, I'm going to be left with only checkpoints that have the highest validation accuracy. Let's go ahead and plot the training and testing curve. So I've given you some code to actually do this. Now, you might have to run this cell twice to encourage the plot to actually show up. But you see, this is exactly what you expect, right? So our training accuracy, just called the accuracy here, goes up to 1 because the model is essentially memorizing the training data set. But the validation accuracy doesn't really improve from, in my case, 0.2, so this might be a slightly different value for you. We can kind of see what's going on here, right? So it kind of plateaus off at 2, and it just takes maybe this one that has the highest validation accuracy. Now let's go ahead and verify that everything I said is actually true. So let's see what's actually in this directory right now. So I'll do lslh model checkpoints best. Let's see what's actually created. So you see just 3 files. Just a checkpoint data, and checkpoint.index. And let's see that this is actually what we want it to be. So we expect that this is going to be the highest validation accuracy. Well, the highest validation accuracy was, as you can see up here, for me was 0.2. For you guys, it might be a slightly different value, but it should be kind of fairly close to that. And let's see. So what I'll do is I'll create a new model. New models get new model. And I'll load the weights on. So I'll do new model dot load weights like this. All right, checkpoint best path. So now load it on the weights. Now let's get the test accuracy for this thing. So get test accuracy, new model, X test and Y test. Now what we'd expect is this is going to be 0.20 for me, right? So it's going to be a different value for you, but you expect this value up here and this one down here to match, right? So I've created a new model, I've loaded on the weights, and I've gotten the test accuracy, and the test accuracy is the same. It's the highest that we got during training, and you can actually verify for yourself that new model and the model before, they really do have the same weights. You can check this for yourself. And again, if you want to tinker around this yourself a little bit, it might be good to just delete these directories that we just created. So I've given you this function again. So if you run this, like I did, it just deletes those directories. So if you want to continue this yourself, you have a clear working space to do that in. In this coding tutorial, you created some more customized checkpoints and used model saving criteria, which help save a model during training only if certain conditions are met. This gives you a lot more flexibility in how to save models. Now it's your turn to play around with this stuff. Can you, for example, create a checkpoint that only saves once every 5 epochs? Or can you, in the section on model saving criteria, increase the size of the small subset of 100 training points to a larger value so that the overfitting is slower? Do these same tricks work? In the next sessions, you'll be learning how to save the whole model instead of just the weights. See you then.
Hi, and welcome back. So far in this week, you've seen how we can include model saving into our training pipeline using the model checkpoint callback, and how you can also manually save the weights of a model using the model.saveWeights method. All of this supposed that you would still have the code to build the model when it came to reloading the weights. Of course, you might also want to save the entire model, weights and architecture combined. That's what we'll talk about in this video. Here's the same model example we looked at last time. Everything looks the same. We're again using the model checkpoint callback, and we're passing it into the model.fit method. This callback will save the model at the end of every epoch. The only difference is in the argument we're passing into the callback constructor. Now you can see we're setting save weights only to be false. So the callback will save the entire model at the end of every epoch, and not just the weights. In fact, this is the default value for this keyword argument, so we could have just left it out altogether. Whenever we save the entire model like this, the files that get saved will change. Remember before, the callback used the file path myModel in the name of the files that were saved in the current working directory. Now, because we're saving the entire model and not just the weights, the file path myModel is used to create a subdirectory within the current working directory. Inside that, you'll find 2 more subdirectories, assets and variables. The assets folder is where files can be stored that are used by the TensorFlow graph. In our simple example, this folder would be empty. The variables folder contains the saved weights of the model. These file names should look familiar from when we were saving weights only. The last file here, savedmodel.pb, is the file that stores the TensorFlow graph itself. You can think of this as storing the model architecture, so it contains all the information from when we built and compiled the model, including the optimizer state, in case we want to resume training from a saved model. Again, we can also save the entire model in the Keras HDF5 format. It looks just the same. We're again setting save weights only equals false. The only difference is we're including the H5 extension as we did before. In this case, just one file will be saved, which here is the kerasmodel.h5 file. This looks the same as when we saved weights only, but this HDF5 file now contains the architecture as well as the weights. We can also manually save the entire model, just as we manually saved the weights of a model after a training run. If you remember, when we saved the weights, we used model.saveWeights. The only difference here is that we're using model.save. This method will now save the entire model, architecture and weights, in the same directory structure as before for the native TensorFlow saved model format. And again, we can manually save the entire model, this time in HDF5 format, just by adding the H5 extension to the file path. So what about loading an entire model? Well, this time we don't need the original code that was used to build the model, so the loading code looks a lot simpler. In fact, this is all there is to it. Here I'm importing the load model function from the tensorflow.keras.models module, and to load the model I just pass this function the path to the model folder, and it will return the complete model instance, architecture and saved weights. We could now do everything that we've done before with this loaded model instance. We could print out the model summary, we could resume training using the fit method, We could run new model.evaluate to evaluate the loss and metrics on a held out test set, or get model predictions from unseen examples using new model.predict. Finally, the code for loading an entire model from the Keras HDF5 format also looks the same. We use the same function, load model, and this time we just pass in the file path, including the H5 extension. Now we have a pretty comprehensive set of tools for saving models in different ways and according to different criteria, as well as loading models. It's also possible to only save the model architecture without the weights, and you'll see how to do that in a reading notebook later in this lesson. In the next coding tutorial, you'll practice saving and loading entire models using the methods we've just looked at.
Just now with Kevin, you learned how to save a whole model instead of just the weights. This is useful when you want to load a model without having to create an instance of it first with the same architecture and compile variables. In this coding tutorial, you'll be doing this for real in your own notebook. Let's open it up now. Okay, so we're working in the same notebook again. Let's go ahead and import TensorFlow. And we're using the CFAR10 dataset again. So let's run this cell, and also let's get this get test accuracy and get new model. Let's import these functions again. And let's go ahead and scroll down to this new section, which is saving the entire model. Now, until now, you've been saving just the model weights, which means that you have to create a new instance of the model and then load the weights on if you want to use them again. And that model, the new instance, has to have the same architecture. You can also save the whole model, by which I mean the weights, the architecture, and even some of the compile variables, such as the optimizer and the loss function. And as Kevin showed you, this is quite easy, right? So let's put this stuff into practice right now. So let's import the model checkpoint as usual. Now let's create a TensorFlow checkpoint that saves the whole model. So before, I would write something like this. I'd write checkpoint path is model checkpoints slash checkpoints. So what this does is it creates a directory called model checkpoints and puts the checkpoints in it. But if you save the whole model, it turns out it creates a directory automatically. So let's go ahead and delete this checkpoints bin. Let's have it just be model checkpoints. You'll see what happens in a second. So it'll actually create a directory with different files in it already. And let's create a checkpoint. So I'll do model checkpoint is, as you're used to, model checkpoint. Let's do file path is checkpoint path. Oops, as we're used to. Now, the big difference is, well, before we had save weights only is true. Now we're going to put it to false. But let's continue saving every epoch. So let's do frequency is epoch like this. And let's put verbose as 1 so we get some sort of print statements. So now we've created this checkpoint. And now we'll play the same game we did before. So I'll do model is get new model like this. And I'll just go ahead and train this model via model.fit. So model.fit, x is x train, y is y train like this. Let's train it for 3 epochs like we're used to. And now we'll enter this the exact same way. So I'll put callbacks as checkpoint like this. Let's go ahead and run this cell. So we're going to train this model. Now again, this might take a little while. So I'll see you on the opposite end of this training session. For me, this model is now finished training. Let's have a look at what's happened. So we've got this one warning, which we can just go ahead and ignore for the moment. But you see, so here it says assets written to model checkpoints as assets. So the model checkpoints is already a directory itself. And above it here, it says saving model to model checkpoints. So let's have a look at what's actually been created. So let's use this kind of trusty line of code that we've seen a few times now. So let's list the contents of this directory. So I'll do lslh model checkpoints like this. See what's in there? And there's 3 things in here. Now these 2, assets and variables, are actually directories. And we have the save model.pb. Now it turns out that the assets directory is empty. You can check this for yourself. But let's look what's actually in the variables directory. So if I do lslh model checkpoints / variables, right, we can look at what's in this directory. See files that maybe look a little bit familiar, right? So before we had checkpoint.data and checkpoint.index, they were roughly the same size. So, it's a little bit less than 200 kilobytes. And this variables was also, I thought, around 2 kilobytes when we were saving just the weights. So you see that inside the variables directory, we save the weights. And the save model.pb is like, it saves the model architecture and how to put the weights back into this model. That's kind of what's going on over here. Let's go ahead and get this model's test accuracy. Let's just call get test accuracy model x test and y test. Let's see how accurate this thing is. 49.3%. So that's my model. Obviously yours will differ a little bit, but we're looking at just under half kind of classification accuracy. What we've done here is we've saved the whole model. We haven't saved just the weights. So before, we had to create a new instance of the model and then load the weights on. But we should be able to create a model from scratch, right? We shouldn't have to create a new instance of it first. Let's go ahead and del model. So I deleted my model here. And then let's check that it actually has disappeared. See, it's not on the namespace. And then I'm going to import from TensorFlow Keras models load model. I'm going to use this function to basically directly load this model. So I'll write model is load model, and then I'll write checkpoint path, right? So this is going to be that directory. And let's also get the test accuracy of this thing. Now what you think is that, well, I've loaded the same model, so it should have the same test accuracy the one I had before. So in my case, that's 49.3. Oops, I forgot to actually run this cell. You need to remember to do that. Let's see and it's 49.3. So for you, these values will be different, but they should still match. And you can again check that this model has the same weights and it actually has the same architecture. So you can check that for yourself if you want. Up until now, we've been saving the model in TensorFlow's savemodel.pb format. We can also do this manually by doing something like model.save. So if I write model.save, and then let's call this my model. This will create a directory called my model with the exact same files that we saw up here. So the save model and the variables. We can also save it in HDF5 format. What we have to do is we put a little extension .h5 at the end. Let's go ahead and save this model like this. And well, let's see what's been created now. So I'll do ls lh my model.h5. Oops, I forgot the underscore like this. And you see this is actually, so this isn't a directory now. This is a single file. And it's my model.h5. You can see some of the information about it, but it's not formulated, or it's not set up like the save model.pb with different directories and stuff. It's just a single file. But let's play the same game. So if I do del model again now, is the model actually gone? We can check that it is. Yeah, so the model is gone. Let's load it from scratch, and we do this the exact same way. So the model is load model like this. So the my model.h5. Let's get the test accuracy for this thing again. So, well, what do we think the test accuracy should be? Well, it should be the same as the one I had before, which I think was 0.493. You can see it up there. Let's go ahead and see if that's actually the case. And it is. So we've reloaded this model. And you can see you can save it in either this TensorFlow.pb format or the Keras HDF5, so .h5 format. And again, as we had last time, if you want to play around with this stuff yourself, it might be good just to clear your workspace a little bit, clear the directory you're working in. So I can delete my model checkpoints and delete my model .h5. So if I just run the cell, it'll do that for me. In this coding tutorial, you saved the full model instead of just the weights. This allowed you to reload a model from scratch, instead of having to create a new instance of it every time and load the weights. It also saves the compile variables such as the loss function and optimizer. It's now your chance to explore this a little bit more. I challenge you, for example, to think about the advantages and disadvantages of saving the whole model versus just the weights, in terms of the speed of loading the model and file sizes. Can you also explore the differences between TensorFlow's .pb format and Keras' .h5 format? In the next lessons, you'll be exploring how to save just the model architecture and how to import existing and pre-trained models from Keras and TensorFlow libraries. See you then.
In this week, you've now seen how we can easily save and load models in TensorFlow, either as part of the training loop or manually. But there are also many pre-trained models available out there that you can download and experiment with in your applications. In this lecture video, we'll take a look at one resource for loading pre-trained image classification models, which is through the Keras API. If you go to keras.io/applications, you'll see a number of different architectures that are available for you to download. These are all image classification models that have been trained on the ImageNet dataset. There are also examples of how you can use these models for different purposes, including as straightforward classifier models or as image feature extractors. Later on in the course, you'll see an example of how to use one of these pre-trained models as a feature extractor, as well as implementing a transfer learning application. Documentation is also available for individual model architectures, so you can see how to use them and what the options are for downloading them. Let's take a look at an example. One of the models available through the Keras API is the ResNet50 model. To load this model, you import the ResNet50 class from the TensorFlow.keras.applications.resnet50 module. Here, I'm creating a ResNet50 object, and when this line of code executes, the model architecture and weights will be downloaded to your local machine if it hasn't already been downloaded previously. When you do this yourself, it might take a few minutes to load in, as these models can be pretty big. Just so you know, the model is downloaded into a hidden folder in your home directory, inside a subdirectory called models. You can also see I've passed in the keyword argument weights equals ImageNet. That means that the model will be loaded with weights that have been learned from training on the ImageNet dataset. Otherwise, if you set this to none, then the weights will be randomly initialized for a fresh training. Another interesting option you can use is the include top keyword argument. By default, this is equal to true, in which case the complete classifier model is downloaded and instantiated. However, if you set include top to be false, the fully connected layer at the top of the network isn't loaded, so what you end up with is a kind of headless model that you can use for things like transfer learning applications. Here's an example of how you can use a downloaded model to make class predictions on any image you might have available locally. First of all, here I've instantiated the model using weights that have been learned from training on ImageNet, and I've set include top to be true, so I'm getting the complete model including the final classification layer. In the Keras module, there are some really useful tools for handling images, and here I'm importing the image module from TensorFlow.keras.preprocessing. I'm using the load image function in this line to load in an image I've got stored in the current working directory called mypicture.jpg. I'm also passing the target size keyword and setting that to 224 by 224. If you take a look at the documentation where we were, you'll see that this is the required input size for the ResNet50 classifier model, and the load image function can handle any necessary resizing for us. The model itself needs to take in a NumPy array as an input, and again the image module can take care of this for us with the image-to-array function. The final thing we need to do to get the image ready for the model is to pre-process it according to the model requirements. You can see here I'm importing the preprocess input function from the TensorFlow.keras.applications.resnet50 module, and the last line of code down here uses that to do that last stage of preprocessing. You'll notice that we're also adding an extra dummy dimension to the input. This might look familiar from earlier on in the course. Remember that the model is expecting a batch of inputs, where the first dimension is equal to the number of examples in the batch. We're just feeding in one example here, but we still need to add the batch dimension for the model. Here is where we get the model prediction, and I'm sure this looks familiar. The image is pre-processed and ready, so we just need to pass it into the model.predict method to get the model predictions. These predictions will be a NumPy array of probabilities, but of course what we want to know is what the classes are that the model is predicting for this image. So the final function that we're importing is the decode predictions function. Again, from the TensorFlow.keras.applications.resnet50 module. This function will take the model predictions and return a list of tuples corresponding to the class code, its description in plain English that we can understand, and the network probability. The top equals 3 argument just means that we're only retrieving the top 3 model predictions. Now you know how to load pre-trained models using the Keras API and use them to get classification predictions on your own images. There are many more models that can be downloaded and used in a similar way through the Keras API, so be sure to take a look again at the website we saw earlier to see all the options. In the next coding tutorial, you'll download and use pre-trained Keras models yourself. So have fun with that, and in the next lecture video, I'll show you another source of pre-trained models we can use with TensorFlow Hub.
Welcome back. As you've seen earlier, you can save Keras and TensorFlow models in various ways. The whole model, just the weights, or just the architecture. But up to now, you've done this only with models you've created yourself. Of course, you can also use such methods to load models that were created by others for use in transfer learning or your own applications. In this coding tutorial, we're going to explore doing this with some models that Keras has built in. Let's open up this notebook now. Before we start coding, let's look through some of the inbuilt models in Keras, referred to as applications. So I'm on this website now, and the URL is given to you in the notebook if you want to follow along. And you see here some of the available models. So let's click on this one. You see some documentation on it, so the arguments, returns, some references as well, and some licenses. And it's a useful website, and it also provides code on how to set these models up, which can sometimes be a bit fidgety. In this coding tutorial, what we're going to do is, let's see if I can scroll up a bit. We're going to essentially follow along this one. So we're going to classify ImageNet classes with ResNet 50. So if you want to pause the video now and have a look around this website to see what interests you, just look around, and when you're ready, we can continue with the coding tutorial. Now that we're in the notebook, let's go ahead and import TensorFlow like this. Now let's click on this number 4, so loading pre-trained Keras models. So click on here. And as I said, today you'll be working with the Keras ResNet 50 model. This is inbuilt in Keras applications. So I provided some code for you that if you on your own machine want to import it, this is the code you have to run. Now on these Coursera notebooks, sometimes they can take a little bit too long to actually run this code since you're downloading a big model. So what I've done is I've downloaded it once and saved it on your workspace already as a Keras HDF5 format. So let's load it in like that instead. So let's import load model. And now write model is load model. Now it's saved as this thing, so Keras ResNet 50.h5. So if you run this, it'll import the model for you. And let's also print model.summary. So let's see, this might take a little bit of a while to run, since it's quite a big model, as you'll see. And let's print the summary. Okay, so now you see what's going on over here. You can see that it's a pretty big model. This is it's got a few more layers than the ones that we've been working with ourselves. It gives us a warning because there's the model wasn't compiled. That's okay, since we're not training it. And there's a lot of layers, but essentially what's going on here is a convolutional neural network where the feature map keeps getting smaller. So the input images are 224 by 224. There's 3 color channels, and it goes down to 230, and then 112, 56, 56 by 56, and it goes down to 28 by 28, then 14 by 14, and eventually 7 by 7, and it finishes with 1,000 neurons. And these 1,000 neurons correspond to the 1,000 classes in ImageNet. So fundamentally, it's not that different from the models we've been working with, right? We've had 10 softmax outputs. This has got 1,000. It's the same fundamental idea, but notice the number of parameters. So it's 25 million parameters. So it's a big model. And let's go ahead and see what are the classifications this model actually gives. So it's trained on ImageNet. So what I've also done is I've added 3 sample ImageNet images to your workspace. So let's see what this model gives as its estimates for what these images are. So it's a classification task. So let's go ahead and just run this cell. So this cell will import those images for you. And I've also provided a function called getTop5Predictions. All it does is it takes the image, it runs the model forward, and then it gives you the top 5 predictions, as well as the probabilities, or the estimated probabilities of those different images. So let's go ahead and display the image. If you type lemon image, it'll show you what it looks like. Now the first time you do this, it might take a little while. You might get some print statement saying it's downloading data from Google. but the second time you won't get that. But you can. So if you need to pause the video, just pause it for a minute. But you see this is a lemon image, and let's see. Well, what does this model actually think this is? So let's go ahead and get the top 5 predictions. So I'll type get top 5 predictions like this, and I'll just type lemon image. Let's see what it gives me. Oops, I must have forgotten to actually run this thing. And let's see if we can get this one again. Takes a little while. Let's see what the things are. Okay, so it's got 5 things, the top 5. Well, consommé turns out is a sort of light French soup. Lemon is in second place, pretty good, right? Because it probably is pretty close. So lemon's in a close second. Eggnog, ladle, and spotlight. You can kind of see what's going on here. So the model has picked up on the fact that there's kind of 2 light yellow circles, essentially. So the estimates are other things that include yellow circles. So consommé, as I said, is a French soup, usually in a circular dish. So it might look a little bit like a lemon in terms of, it's a light circle. Lemon, obviously, but eggnog, ladle, and spotlight. So these are all kind of bright circles. You see what the model's doing here. Let's see what happens with the second image. So let's type viaduct image, which, as the name suggests, is a picture of a viaduct. And what are the top 5 predictions for this thing? So let's do get top 5 predictions like this. Viaduct image. Well, what does this model think it is? Vault, prison, viaduct, window screen, and fire screen. And again, you can kind of see what's going on, right? So it's noticed that it has these kind of vertical slats. The estimates are all things that have that as well. So a vault obviously has that. We can tell it's not a vault because it's outside. You can see the sun. But prison, you can kind of see what the model's doing here. And let's go ahead and let's look at this third one. So this is an image of a water tower. And this one is actually a little bit, it's pretty difficult. So this is a water tower photographed from below. And you can say, even for a human, I'd say this is pretty difficult to classify correctly. So I personally think it looks a little like Sputnik, which is the first artificial satellite put into space by the Soviets. Let's see what this model thinks it is. I don't think Sputnik is one of the categories, but let's see what the top 5 predictions are for this thing. So get top 5 predictions, water tower image. Let's see what this model thinks. So it says solar dish, ladle, planetarium, strainer, and jigsaw puzzle. So water tower isn't even in there. You can kind of see what's going on with the solar dish. You can imagine pictures of a solar dish might have a kind of white, gray circle with a blue background. So that's maybe why it thinks it's a solar dish. A ladle, again, is a sort of round object with a stick. So you can imagine why it thinks that. Planetarium, strainer, jigsaw puzzle, I'm not really sure why it thinks that, although it's a fairly low probability. So it struggles with the water tower. But then again, I think humans might also struggle to identify this correctly as a water tower. Let's have a quick review. In this coding tutorial, you loaded a pre-trained model from Keras applications and used it to at least attempt to classify images from the ImageNet dataset. It's now your chance to build on this work. Can you, for example, load a different Keras applications model and compare the classifications it gives with the ResNet 50 model we just used? In the next session, we'll look at doing the same thing, but with TensorFlow Hub, which also contains a large library of publicly available models and model components. See you then.
Welcome back. There's one more resource for pre-trained models that I'd like to cover in this week, and that's TensorFlow Hub. TensorFlow Hub is a little different to the pre-trained models we saw last time that we loaded through the Keras API. TensorFlow Hub is more focused on network modules, which you can think of as being separate components of an overall TensorFlow graph. You can visit the TensorFlow Hub page at tensorflow.org/hub, and one of the first things you'll notice is that TensorFlow Hub is actually a separate library, so if you want to use it, you'll need to install it. Here you can see that it's easy to install TensorFlow Hub using pip, and the namespace that's used throughout the site is here. We're importing TensorFlow Hub as hub. You can click over here to browse the available modules in the library. And one natural way to search for modules is by problem domain. So let's take a look at the image modules. Here you can see some of the modules that you can download, and each module has a label such as image feature vector, image classification, or image generator. So there are some complete models here, as well as modules or components that you might want to use as part of a bigger network model. Let's look at an example. Here you can see an Inception ResNet model, which is an image classifier. The library is pretty well documented on this site. For example, this page tells you a bit about the model and the research behind it, and down here it shows you how easy it is to use the module. We can just import it as a hub.keras layer object and use it in just the same way as we would any other layer as part of a sequential model. The final stage builds the model and sets the image size. Now the model is ready to use in just the same way as our other TensorFlow models. You should take some time to explore for yourself the different modules that are available on TensorFlow Hub. Even within the image domain, there are several different types of network model, and as you saw, there are also modules you can download for text and video domains. In the next coding tutorial, you'll practice using TensorFlow Hub for yourself by downloading and running an image classification model.
Welcome back. In the last video, Kevin introduced you to TensorFlow Hub, where you can download parts of deep learning models called modules for your transfer learning or for your own applications. In this coding tutorial, you'll be loading one of these modules and using it to classify the same ImageNet pictures you saw last time. Let's get started. Before we start coding, let's have a quick browse through some of the available models on TensorFlow Hub. We'll start on the TensorFlow Hub webpage on the main TensorFlow website, which you see here. And this link is provided in your notebook if you want to follow along. And we'll click on this button, so Browse Modules, and then we actually see what modules are available to us. Let's go ahead and click on this. And we've been working with image classification usually, but you can see some of the filters that you see here. So let's go ahead and click on Image. And now you see some of the problem domains. Now we want to do image classification. So what I'll do is I'll just click away these ones. So all we'll have to do is image classification. See how more and more models are disappearing. You can also filter on things like the architecture, the sort of data set's been trained on. You kind of get the idea here. Even the saved model format. And let's look at this first one. So it's called ImageNet MobileNet V1 050 160. Let's go ahead and click on it. A little bit like the Keras Applications webpage. We see some information about it. So it's saved as a TF2 saved model format. We see an overview, how it's been trained, how you can use it. This is how you can actually load it for your own use. And you get a little bit more information. Let's go ahead and use this model to classify images just like we did with the Keras applications. Let's go to the notebook and let's get started. So once we fire up this notebook, let's go ahead and load and import TensorFlow like this. Let's press on 5 when that's done. So we're going to go to number 5, TensorFlow Hub modules. What we're going to do now is we're going to play the same game we did with this Keras Applications model with this new TensorFlow Hub Google MobileNet V1 model. So we're going to take the same 3 images and see, well, what does this model think that these images are? How does this model classify this? And again, actually loading this module in from TensorFlow Hub can sometimes take a little bit too long on these Coursera notebooks. So what I've done is I've already saved a version of the model on your working space, and we're going to load that one in instead. But here, this code, you can use on your own machine to actually load in this model in exactly the same way. So let's go ahead and load in the module first. All right, module is load model. Oops, I need to run this one first. And then I'll do module is load model. It's going to be models. So it's saved in a directory called models, and it's called TensorFlow MobileNet V1, and it's saved in one of these TensorFlow saved model formats. I'll do it like this. Now let's go ahead and turn this into a model. So turn this into a Keras sequential model. I'm going to use a help.keras layer to do this module. And let's go ahead and build this model. We'll discuss in a second exactly what's going on here. Let's go ahead and do the input share we have to specify. This is 160 by 3. And let's go ahead and print a model.summary this time again. So let's see what happens when we run this. So this might take a little while, but what's happening is, right, so we have this module. We make it into a sequential model. So this is essentially a model that contains this module. And then what it gives us is model summary. Well, it's actually only got one layer according to this thing, right? So this is one Keras layer with 1.3 million parameters. So it's got quite a bit fewer parameters than last time. So the Keras application model had 25 million. But also the Keras application model had this huge long model.summary with many layers. This one looks like it's only got one layer. That's of course a bit of a simplification. So it's because we have a module which becomes a layer. It looks like it's only one. And notice how all these parameters, 1.3, they're actually all non-trainable. So for the other model, almost all the parameters were trainable. So we can only use this model to do forward passes with. That's okay for the moment. Now let's go ahead and play the same game. So I'm going to load in the same 3 images. So this is the code to do that. Remember, there was a lemon image, the viaduct image, and the water tower image. And the only difference is that the target size is a bit different than last time. And that matches, see, 160, 163. That matches this thing, because this thing has got 3 channels for the RGB colors. So let's go ahead and load this thing in. And this is one line of code which I've provided for you, which just changes the ImageNet categories from a numeric value, so 0 to 999, to human readable formats. Let's go ahead and read that one in as well. This one, by the way, is provided. If you go to the TensorFlow Hub page for this model, it's provided as well. And again, I've provided this get top 5 predictions function for you. So what it does is it takes an image and it just returns the top 5 predictions. No probabilities this time, but we can still see the top 5 predictions. Let's go ahead and define this. And now let's see what the predictions are. So if I type in lemon image, we can remind ourselves what the lemon image actually looks like. And see what are the top 5 predictions for this thing. So get top 5 predictions of the lemon image. So let's see what does this model think that this lemon is. Scroll down. So number 1 is shower cap. Number 2, tray. Number 3, candle. Number 4, brassiere. And number 5, African chameleon. So it struggles with this a little bit. So let's see. It seems to have struggled with the lemon a little bit. So let's see what it does for the viaduct and the water tower. So let's go ahead and do viaduct image. Let's see what this one looked like again. So now you remember this one. It's a viaduct, some open sky in the background. And let's see what does this model think that this thing is. So get top 5 predictions, viaduct image. And this one it does really well on. So it says viaduct, pier, dam, prison, solar dish. But viaduct is in first place, so I'd say that's pretty good. It definitely knows it's a viaduct. And again, it kind of notices that it has these vertical slats, right? Periodic vertical slats. So viaduct, pier, prison, dam maybe a bit less, but you can kind of see how a model might think that picture is something like a pier or a prison. Now let's go to this water tower image again. So do you remember the water tower image from last time? Now, it's quite a complicated image, right? So again, I think it looks a little like Sputnik, that Soviet satellite. Maybe even humans would struggle to see that this is a water tower and not, I don't know, something else, some sort of dish or something. So let's see what this MobileNet model thinks this thing is. I'm going to get top 5 predictions of water tower image. Solar dish, water tower. So it gets water tower correct as number 2. That's pretty impressive because the Keras applications model really struggled with this. Solar dish you can kind of imagine, right? So it's kind of a gray thing with blue in the background. You can imagine that other solar dish pictures might look like that. Aircraft carrier, jigsaw puzzle, and oxygen mask. I'm not really sure where those come from, but pretty impressive that water tower is number 2. That's the end of this coding tutorial. Good work. Now that you've learned about TensorFlow Hub, the possibilities are endless. We've only scraped the surface. There are models for text and video as well, ranging from classification to generation to prediction. Try to download some other ones and use them, or incorporate them into your own work. This is also the last coding tutorial for this week and for me. Great job getting through it. I hope you enjoyed it, learned a lot, and will get a chance to put this into practice later. See you then.